The deeper we stare into space, the stranger it becomes. For all the charts, models, and simulations we've built, the universe still throws curveballs. Anomalies so bizarre they make scientists question the rules of physics themselves. From signals with no source to gravitational ripples without collisions, NASA and global space agencies have uncovered a catalogue of cosmic mysteries that simply don't add up. The radio signal from beyond the Milky Way. It started out as a whisper, just a small burst of energy hidden in years of data from radio telescopes. They almost missed it, the astronomers. It looked like a bug at first, but then there was another, one more. Each signal came from a direction far beyond the Milky Way and was milliseconds fast and very strong. FRBs stand for fast radio bursts. Even though we've found hundreds so far, FRB 121102 was the first one that was proven to repeat, which caused a lot of excitement in the scientific community. The signal wasn't just odd, it came from a 3 billion light-year distance dwarf galaxy that is very old. No one could say why. A typical FRB lasts just a few thousandths of a second, but in that tiny moment, it can release more energy than our sun produces in an entire day. That's the cosmic equivalent of hearing a match strike and realizing it lit up an entire city block. When FRB 121102 repeated, meaning it wasn't a one-time cosmic explosion, it overturned everything scientists assumed about these phenomena. This wasn't a dying star's final flare. Something was producing it, repeatedly, reliably, intentionally. Where the signal came from? A very small and faint galaxy that looks like a dried-out spark next to the Milky Way. That fact made the mystery even stronger. Why would something so bright and full of life come from a place where there isn't much going on? Scientists thought that these kinds of loud signs would come from the busy, dense centers of galaxies, or from black holes in galaxies that are colliding. But FRB 121102 came out of a pretty quiet part of the universe, like thunder in a field that was empty. Then came the polarization, a twist in the signal's wave pattern. This meant the burst was traveling through an incredibly strong magnetic field, one far stronger than anything expected in that region of space. It suggested the FRB might be near a neutron star, or possibly a magnetar, an ultramagnetic corpse of a star. But even that didn't explain the power, or the repeating pattern, or the pinpoint location, which seemed embedded in something scientists couldn't clearly resolve. NASA joined the fun. This was also true for radio systems around the world, like Arecibo, Chime, Green Bank, and VLA. The Very Large Array in New Mexico made an amazing map of the bursts and tracked them to a part of the dwarf galaxy where stars are being formed. But that made us wonder even more. Was this thing a neutron star inside a dense nebula? Did the young magnetar send energy out into space as it spun quickly? If that's the case, why did it produce so much more energy than what is possible theoretically? Some signals showed intervals that resembled a heartbeat, pulsing every 157 days, with short periods of frenzied activity followed by silence. And that pattern didn't just repeat. It persisted for years. This wasn't random. It wasn't noisy. It was a clock. Something far away was ticking in perfect rhythm, and nothing we knew could explain how or why. A lot of theories came in. Some people mentioned a binary system with a magnetar going around a huge black hole and only exploding when it passed through certain patterns. Others suggested a new type of star object that we hadn't seen before, something in between a neutron star and a quasar. Strangest ideas, though, got the most attention. Could it be made up? Were FRBs being used by some kind of alien mind to send messages across galaxies? No official institution claimed that publicly, but many researchers admitted privately that the precision and energy of the bursts were puzzling, uncanny, even unsettling. It wasn't just the power, it was the intent. These weren't like the one-off explosions of dying stars. They repeated, they pulsed, they were consistent. And then came something even stranger. Other repeating FRBs were found. FRB 180916 showed a 16-day cycle, and unlike 121102, it came from a spiral galaxy much closer to Earth. Now, the question was bigger. Are all these bursts the result of the same mechanism? Or are we looking at a family of cosmic phenomena we barely understand? NASA launched follow-up investigations using both space and ground-based telescopes, hoping to triangulate signals across multiple wavelengths: radio, X-ray, infrared. But so far, no accompanying light, no visual fireworks has ever been directly linked to these bursts. They arrive, blast our detectors, and vanish. The deeper question is this: if energy this powerful can reach us from galaxies 3 billion light-years away, what else could be out there, hiding in frequencies we haven't even begun to monitor? The FRB story has taught scientists one humbling truth: space is a noisy place, and most of that noise is still undeciphered. There is still talk from FRB 121102 right now. There are more and more signs, and they still can't be explained. Stars have been ruled out. Comets have been ruled out. They have ruled out getting involved. Whatever it is, it's real, it keeps happening, and it's not from here. Voyager 1 sent back data that defied physics. This wasn't what Voyager 1 was meant to do. Over 15 billion miles away from Earth, it had already gone beyond all expectations after almost 50 years of travel. Voyager 1, which was launched in 1977, was the first person sent by humans into space between the stars. It flew by Jupiter and then Saturn, finding new moons and taking pictures that will blow your mind. In the end, it went past the heliopause, which is the unseen line where the sun's impact ends and deep space begins. Then, in 2022, it sent back something strange. The data coming from Voyager 1's Attitude Articulation and Control System, AACS, didn't make sense. This is the system that tells the spacecraft how to orient itself, where to point its antenna, how to stay aligned. It's like the gyroscope in your phone, but far more precise and infinitely more vital in the vacuum of space. Without it, Voyager 1 can't keep its high-gain antenna aimed at Earth, and for some reason it started transmitting nonsense. The telemetry data showed the AACS was functioning. It was keeping the antenna pointed correctly, but the information it was sending about its own status, temperature, voltage, direction, was completely incoherent. The readings made no logical sense, as if Voyager's mind had split from its body. Even stranger, no onboard fault was detected. The spacecraft wasn't in safe mode. Its signal remained strong, but what it was saying didn't match what it was doing. Think about that. You're driving a car. It's moving just fine, staying in its lane, but when you check the dashboard, the speedometer says you're going 900 miles per hour. The fuel gauge spins in circles. The GPS insists you're underwater, but you're still cruising down the freeway. That's the situation NASA found itself in. And the deeper they dug, the more puzzling it became. Was it a software glitch? Maybe radiation scrambled Voyager's ancient memory? Could cosmic rays, high-energy particles flying through space, have flipped a bit or corrupted a subsystem? These ideas were floated, but there was no evidence of hardware failure. And rebooting the system remotely is risky. If you send the wrong command, Voyager 1 could stop talking to Earth forever. NASA's team began troubleshooting. Slowly, carefully. Remember, Voyager 1 is so far away that it takes nearly 45 hours to send a signal and get one back. 22.5 hours each way. Imagine debugging a computer that responds once a day. That's the reality of deep space engineering. You don't get second chances. Then came the most baffling theory of all. What if the spacecraft was sending telemetry from a different part of its system, one it wasn't even supposed to use? That would mean it had silently rerouted its own data through another channel, something never programmed into its software. In other words, Voyager 1 might have improvised. Let's pause there. This is a spacecraft launched during the Carter administration. Its computing power is less than a digital wristwatch. Its memory is measured in kilobytes. It was built before the internet, and yet it may have figured out how to keep communicating by using parts of itself in ways no engineer intended. That's not just impressive, it's borderline eerie. Eventually, months later, NASA announced that Voyager 1 was indeed routing data through an old, defunct computer, one not used in decades. The spacecraft had apparently begun using this outdated system without informing Earth. No one knows exactly why. The team suspects it was the result of a chain reaction inside the AACS, possibly triggered by a single flipped bit or hardware degradation after decades in deep space. But even that's just speculation. This is where the science rules become less clear. As of now, Voyager 1 is no longer affected by the sun. It's working in interstellar space, which is colder, darker, and farther away from other places we've sent robots. The particles, radiation, and forces outside of our solar system don't act the same way they do inside. There might be new kinds of disruptions happening because of these situations. Or are we finally hitting the end of what our technology can do in space? Some scientists even floated speculative ideas: quantum interference, exotic particles, or unknown forces interacting with Voyager's systems. While those remain on the fringe, what's undeniable is that Voyager 1 did something no one programmed it to do, and it managed to stay alive and talking the whole time. Eventually, engineers reconfigured the spacecraft to resume proper telemetry by instructing it to use the working system again. But the incident is now legendary among mission controllers. It's a moment where the universe reminded us, even when you build something to be predictable, space has its own plans. Voyager 1 continues to travel outward, inching deeper into the unknown, now in its 47th year of operation. It still whispers to us across a vast gulf of time and distance. And sometimes, what it says doesn't just challenge engineering, it challenges what we think machines can do. The unmapped object near the edge of the heliosphere. They don't mean a sharp wall or a bright line when they talk about the edge of the solar system. The heliosphere is what they mean. It is a huge bubble made of solar wind and magnetic fields that the sun inflates and stretches billions of miles in all directions. It keeps us safe from cosmic radiation and separates our space from the space between the stars. Spacecraft like Voyager 1 and Voyager 2 have been slowly moving toward and now through that line for decades. On the other hand, in 2018, their sensors picked up a signal from an object that didn't fit. Both Voyagers carry low-energy charged particle (LECP) detectors, tools designed to sense changes in the energetic particles that fill the heliosphere. As they neared the heliopause, the final boundary before interstellar space, they began reporting strange fluctuations, not just in radiation, but in the direction and density of incoming particles. These changes suggested the presence of a solid or semi-solid body near the outer edge of our solar system, one that had never been mapped, observed, or predicted. The region in question lies between 120 to 130 astronomical units from the Sun. That's 11 to 12 billion miles away, far beyond Pluto. In this zone, space should be relatively uniform. Voyager 2, which entered interstellar space in 2018, was expected to record a smooth transition as it pierced the heliopause. But instead, its sensors detected a localized distortion, as if a large object was bending the magnetic field around it. The thing didn't give off any light. Infrared or visual devices couldn't see it. Its magnetic and gravity pull were clear though. It's like driving on a smooth road and all of a sudden hitting a patch of rough terrain. There are no cracks in sight, but your car shakes like a huge object just went by nearby. This led some researchers to propose the existence of a hidden planetary mass object, possibly a rogue planet or large icy body hovering near the heliopause. The idea isn't new. Planet 9, a hypothesized Neptune-sized object in the outer solar system, was proposed based on similar gravitational effects. But this new anomaly was in a different place and moving in an unexpected trajectory. Worse, it didn't match any known orbit. It wasn't circling the Sun in a way typical of distant Kuiper belt objects or scattered disk bodies. It seemed to drift, like a foreign object just passing through. Not captured, not bound, and not behaving. When NASA and JPL tried to model the Voyager data, the numbers kept spitting out something uncanny. The source of the distortion was massive, but not dense. Not a black hole, not a star, not even a moon. More like a cloud-wrapped object, possibly coated in reflective ice or made of exotic matter. Something unlike anything else in the known system. Space telescopes like WISE and Spitzer were checked for any thermal signatures in that region. Nothing. It was like trying to photograph a shadow that wasn't casting any. And yet, the magnetic field distortions didn't go away. They lingered, and they moved. Could this be a frozen interstellar object like Oumuamua, but far larger, maybe? Oumuamua shocked astronomers in 2017 by being the first confirmed object to enter our system from another star. But this new anomaly wasn't zipping past. It was lingering at the edge, almost waiting. The conspiracy theories arrived quickly. Was this a probe? A concealed ship? A cloaked satellite? Scientists, of course, dismiss these claims, but what they can't dismiss is the data. The field lines bent. The particle flow changed. Something is there. It's not the only one. Later, IBEX, the Interstellar Boundary Explorer, a spaceship watching the edges of the heliosphere from Earth's orbit, found blips that were the same as those seen by Voyager 2. IBEX confirmed that strange releases, known as ENA flows or energetic neutral atoms, were coming from the same area. This added weight to the idea that a large object, maybe hundreds of kilometers wide, is interacting with the heliosphere at its weakest point. Some even suggest it could be the outermost member of our solar system, a planet-sized ice body that formed alongside Neptune and was ejected outward long ago, now circling at the very edge in a ghost orbit we never thought to check. Or it could be something alien to our system entirely, not part of our formation history, not even gravitationally bound to our Sun. The Interstellar Mapping and Acceleration Probe, IMAP, which is about to take off, could give us the best chance of getting a better view. It has tools that are meant to find and fix ENA problems with a lot more accuracy than IBEX. Until then, the edge of the solar system will stay a border, full of plasma streams, magnetic walls that move, and now the possibility of a visitor we did not expect. Dark matter disruption detected in an empty zone. There are places so empty in the vastness of space between galaxies that they are known as cosmic gaps. These are huge areas of space with almost no matter, no stars, and no structure that can be seen. Things should go smoothly in these places. Not any light, no motion, and no excitement. Not so in 2020, when a NASA-funded group of scientists looked at gravitational lensing patterns in a known void. They saw something that didn't make sense. The gravitational field of an area with no obvious mass suddenly became distorted. It started with data from the Hubble Space Telescope and the Dark Energy Survey. Researchers were mapping how light from distant galaxies bent and stretched as it passed through foreground space, a method called weak gravitational lensing. This process allows astronomers to detect invisible mass, like dark matter, by the way it warps space itself. Typically, these distortions follow predictable patterns, but in one region, an allegedly empty area between two galaxy clusters, the lensing map showed a sharp localized warp that appeared and disappeared over several months. It does not make sense. Dark matter doesn't give off, reflect, or take in light by definition, but it does have mass, and that mass should stay the same. It doesn't get worse. It doesn't beat. It doesn't move all of a sudden. Still, the data showed a changing lensing signature, as if a huge unknown object had moved across the field of view and then disappeared. Astronomers ran the models again. Same result. The light from galaxies behind the void had briefly bent, as if tugged by an invisible hand. When checked against known catalogues, there were no galaxies, no black holes, no gas clouds, no rogue stars, nothing that could explain the shift. It was as if a chunk of gravitational influence had passed by, completely dark. Some speculated it could be a dark matter clump, a dense cluster of the invisible stuff passing through space. But dark matter, based on all previous data, doesn't usually form in such isolated pockets. It tends to surround galaxies or filaments in the cosmic web, not wander through voids on its own. Another, scarier idea was that this could be a dark matter wave, which is a ripple in the universe's structure of unseen mass caused by something we haven't found yet. If this is true, it means that dark matter isn't fixed and can move through space in concentrated ways, like wind gusts in a storm that we can't see. That's really scary, because it means that the rules we use to understand mass, motion, and how gravity works might not be full. NASA's Nancy Grace Roman Space Telescope, due to launch soon, is designed in part to explore exactly this kind of phenomenon. With more sensitive instruments and better wide-field resolution than Hubble, it may help pinpoint these shifting gravitational ghosts. But for now, all we have is a single piece of hard evidence: gravity-bent light in a place where nothing visible should have been able to do that. Some fringe physicists even posited the idea of a dark matter soliton, a hypothetical particle wave structure that moves through space like a self-contained ripple, distorting space-time as it travels. If that's true, we might not be dealing with matter at all, but with a moving fluctuation in gravity itself, a distortion created by the universe's unseen scaffolding. Could we have seen something really strange go by, like a primordial black hole or a piece of physics from before the Big Bang? We missed something so small and dark that not even our best tools could see it, but with enough mass to bend space-time as it went by. The findings are now part of the science record no matter what. A moving ghost mass went through an empty area. What it left behind was a scar in the shape of bent stars. It didn't leave behind any light, radiation, or residue. If this is just one change caused by dark matter, how many more are going on right now, in places we can't see? What number of gravity distortions do we not see because our cameras have blind spots? What does it mean if the world changes and moves around more than we thought? At this point, experts can only watch, drawing, waiting. We're on the verge of a new type of physics that doesn't even have rules we know about yet if dark matter can move and move in ways that make it look like mass without having any shape. Pioneer Anomaly, the spacecraft that slowed without reason. NASA sent Pioneer 10 and 11 into space in the early 1970s with two goals in mind: to explore the outer planets and then glide into space between the stars. They mostly did what they said they would do. In 1973, Pioneer 10 flew by Jupiter. The next mission, Pioneer 11, flew by Saturn in 1979. After their tasks on planets, both ships kept going out into space, being quiet, dependable, and loyal. For a while they were. By the 1980s, mission engineers began noticing something strange. Both Pioneer 10 and 11 were slowing down, just slightly, as they left the solar system. It wasn't dramatic. It wasn't a crash or a failure. It was subtle, about 8.74 x 1010 meters per second squared, a number so small it might seem meaningless. But in the precise world of celestial mechanics, that number was a scream. You see, deep space navigation is ruled by Newton's laws. A spacecraft once launched and left alone should continue on its path at a steady speed unless acted upon. Every movement, every acceleration, every deceleration, it all has to be accounted for. And with Pioneer, something didn't add up. There was no known source for the deceleration. It was like space itself was holding them back. Scientists double-checked everything. Could it be solar radiation pressure? No. The effect was too persistent, and it continued long after the sun's influence had faded. Was it gas leaking from the spacecraft? That would have shown up in attitude data, and there were no signs. Could the onboard radio systems be pushing them back? Unlikely, and the calculations didn't support it. Still, the strange thing kept happening. For many years, scientists were pretty scared when they heard about what they called the Pioneer anomaly. Because if something as simple as Newtonian motion wasn't working the way we thought it would, then either our models were wrong or the ship was being affected by something new. Theories piled up. Some thought it was a thermal recoil force, essentially heat emitted from the craft's power systems, causing a tiny push in the opposite direction. Others proposed more exotic ideas, modified gravity theories like MOND, modified Newtonian dynamics, or even an interaction with dark matter or unknown spacetime properties in the outer solar system. One group suggested the craft were entering a region of altered spacetime, where time and gravity behave differently. Another proposed the possibility of an undetected planetary mass, something like a hidden dwarf planet, tugging subtly on the spacecraft. But those ideas lacked evidence, and still the anomaly remained. In 2012, a partial explanation emerged. A detailed thermal analysis showed that some of the deceleration could indeed be caused by uneven heat radiation from the spacecraft's radioisotope thermoelectric generators. Essentially, heat from the onboard systems was bouncing off parts of the spacecraft and creating a faint but constant backward push. It made sense. It accounted for some of the anomaly. Even today, there remains a discrepancy, small but persistent, between the modeled forces and the observed motion of the Pioneer spacecraft. In the vacuum of space, where everything should behave like clockwork, Pioneer 10 and 11 still tell us a different story. One of resistance, one of subtle warping. No other spacecraft has replicated the anomaly quite like Pioneer. Not Voyager, not Cassini, not New Horizons. Some say it's because those missions had different configurations or flight paths. Others wonder if something unique about the Pioneer twins, their shape, their materials, their spin stabilization, interacted with space in a way we didn't anticipate. Maybe they just happened to walk by something that the other people didn't see. The Pioneer anomaly is still one of the most interesting riddles in space travel that hasn't been solved. It is where engineering, physics, and astronomy all meet. Any machine, no matter how well it behaves, can run into the unknown, and in the silence of deep space, even the faintest sound of resistance can be heard like thunder. Pioneer 10 and 11 are no longer making noise. It's been years since their last broadcast. Infrared blips from a supposedly dead star field. There are empty spots in the sky at night. It's not that there's nothing there. It's just that what was once bright has gone out. Astronomers call these places dead star fields. They are places where supernovae have already happened, stellar fuel has been used up, and what's left are white dwarfs, neutron stars, or cold debris from the stars. Most of the time, these areas are quiet across the board. But in 2019, a scan of the very far sky saw something flashing in infrared light where it shouldn't have been. The data came from the WISE telescope, NASA's Wide Field Infrared Survey Explorer. WISE is designed to spot heat, even from incredibly faint or distant objects. When scanning a known cold region, previously catalogued as devoid of active stellar activity, WISE detected 3 distinct infrared flashes, spaced irregularly over a span of 36 days. Each flash lasted just hours, then disappeared. This wasn't just a sensor glitch. Multiple instruments confirmed the readings. Follow-up observations with the Spitzer Space Telescope and ground-based arrays showed residual warmth in the area, but no central source. There was no star, no brown dwarf, no protoplanetary disk, just faint ripples of infrared light, as though something invisible had flared up, then cooled just as fast. What could make a place hot when it shouldn't be? The first idea was that micrometeoroids were falling into each other and releasing heat energy. The size was wrong, though. These blips gave off more energy than any 2 that small of space rocks could. Another idea was that an exoplanetary body that had not been seen before had broken down, but once more there was no star in orbit to explain its appearance. Some physicists suggested the flashes might be the signature of Hawking radiation, the hypothetical evaporation of micro-black holes. These black holes would be ancient, smaller than an atom, and near impossible to detect, until they decay. If one did, it would release a sharp burst of radiation, just like what was observed. But no one's ever seen that happen before, and confirming it would require observing another one. Another possible culprit: dark matter annihilation. Certain dark matter models propose that under specific conditions, dark matter particles can collide and annihilate each other, releasing energy in the form of heat or gamma rays. But for that to occur, there has to be enough dark matter density in one location. And this dead field wasn't previously on any high-density map. Others suggested a transient event from a rogue planet, a massive object drifting through space without a star. Maybe it had a volatile atmosphere or internal geothermal activity that triggered sudden outbursts of heat. But again, WISE couldn't detect any mass large enough to support that theory. There's also the possibility of artificial origin. Not aliens, but spacecraft. Could these flashes have been the heat signatures of some distant, unknown object maneuvering silently in the dark? A comet from another system firing off volatile gases? A heat leak from something we didn't launch, but someone else might have? We really don't know. NASA made a list of the strange things it saw, marked the area, and planned to look at it again with the new Nancy Grace Roman Space Telescope. With its high-resolution infrared powers, that camera might finally be able to get a clearer picture of what's up there. No one can explain the flashes until then. They are just short, quiet waves in the void. Take a look at that. Something warmed up, lit up, and went away somewhere in the sky that wasn't visible to the naked eye and wasn't shown on any of our star maps. Not once, but 3 times. It wasn't noise. That was a sign. Heat-based ink with a message. Something that blinked in the dark didn't leave a trace. No space. There is no light curve. It was only a short heat signature, but it was strong enough to make us question our ideas about where action should and shouldn't happen. The Great Cold Spot in the cosmic microwave background. The universe gave off the faint glow we now call the cosmic microwave background, or CMB, when it was only 380,000 years old, which is very young in cosmic terms. There is an afterglow from the Big Bang that covers the whole sky and has a temperature that changes by only about 1 part in 100,000. You can expect these small differences. They set the stage for later galaxies, stars, and planets. That was not the case in 2004. A different part of the sky showed a huge cold spot called the Great Cold Spot. Detected by the Unmapped satellite and later confirmed by ESA's Planck spacecraft, this region was significantly colder than the surrounding CMB. While typical cold areas dipped by microkelvins, fractions of a degree, this one dropped nearly 70 microkelvins below the average. That might sound small, but in the precise language of cosmic structure, it's as bold as a red X on a treasure map. At first, scientists thought it might be a statistical fluke. The universe is random after all. Given enough sky, one patch could just coincidentally be colder. But the shape of the cold spot wasn't random. It was round, smooth, and sharply defined, like a bruise in the fabric of the early universe. And its scale was jaw-dropping, spanning over 500 million light-years across. That's a void bigger than anything we expected to find. One early explanation was a supervoid, an enormous underdense region in the universe where there are fewer galaxies and matter than average. The idea was that light from the CMB passing through such a void would lose energy through a process called the integrated Sachs-Wolf effect. As photons fall into a gravitational well and then climb out, they can lose some energy if the void is expanding, leaving them cooler when they arrive at our telescopes. But the problem? The observed cold spot is too deep to be explained by any known supervoid. Surveys of the area, including galaxy counts and redshift measurements, confirmed there is a void in that region, but not big enough or empty enough to account for the full temperature dip. It's like blaming a leaky faucet for flooding a house. The math just doesn't work. Some theorists turn to more exotic explanations. Could the cold spot be a sign of cosmic texture? These are theoretical defects in space-time that may have formed in the early universe when fundamental forces split apart. Think of them like wrinkles in a tablecloth after it's been stretched too quickly. A cosmic texture would create a spherical imprint on the CMB and a temperature drop. The Great Cold Spot fits the shape and depth, making it one of the few potential signatures of this elusive physics. Others raise the possibility of quantum entanglement with another universe. In some versions of the multiverse theory, bubble universes could collide in the early inflationary epoch. If one brushed up against ours, it might leave a permanent scar, like the cold spot. But this idea, while dramatic, is almost impossible to prove. The data simply isn't fine-grained enough to distinguish a universe-to-universe collision from more mundane physics. The cold spot is still one of the biggest strange things in the universe that scientists have ever seen. Our usual view of the universe doesn't fit with this. It's too cold, too big, and too tight. No matter how much we study, we still don't know what caused it. Some experts have even said that our knowledge of gravity on very big scales may not be complete. If gravity acts differently at different lengths in space, it could change how energy moves through space and how photons from the CMB change as they travel to Earth. That is, the cold spot might not be a random spot in the sky. It could be a sign that our whole view of the world needs to be changed. Instruments like the Simons Observatory and future CMBS-4 telescopes will provide much sharper maps of the microwave background. These may finally reveal whether the cold spot is truly unique or just the most dramatic example of a broader misunderstood phenomenon. In the meantime, the Great Cold Spot remains chilling, in both real and figurative ways. It's a look into the past, an old drop in the first light of the universe that no one can explain. Astronomers have been interested in and frustrated by it for 20 years, not sure if it's a cosmic mark, a flaw in space-time, or a ripple from beyond. A perfect circle of galaxies with no known cause. You would expect order in deep space, but it's a mess. Huge amounts of gravity chaos over billions of years have caused galaxies to group together in filaments, spin in clusters, and spread out across empty spaces. Wildlife isn't always neat. In 2021, when scientists using data from the Sloan Digital Sky Survey said they had found a perfect ring of galaxies covering more than 1.3 billion light-years, it stopped everyone in their tracks. The structure is called the Giant Arc, and it's unlike anything else we've seen. Imagine a faint, sweeping crescent of galaxies and galaxy clusters, each separated by millions of light-years, yet forming a near-perfect curve. This wasn't just a fluke of projection or a chance alignment. Multiple independent analyses confirmed its arc-like geometry. The issue is that this shouldn't exist in our current understanding of cosmology, especially in light of the cosmological principle, which says that the universe should generally look the same in all directions at big scales. One of the most important ideas in modern astronomy is the cosmological principle. It assumes that matter in the universe is spread out evenly on a large enough size. There shouldn't be a side with more organization than the other, but the giant arc doesn't follow this. It's way too big, too planned out, too planned out. The arc itself measures about 1/15 of the observable universe across. That's not small, that's enormous. Its curvature suggests it's not simply a linear alignment, but a true arc in three-dimensional space. And every galaxy and cluster within it appears to share a common redshift, indicating they're all at roughly the same distance from us, and likely formed at around the same time. So how could something so big and well organized come into being in a world where everything is random? One idea is that it's just a random accident, an event with a very low chance of happening, but not impossible in a world with no end. But computer models of how the universe evolved don't make shapes like the giant arc. Not if you use normal physics. Not until the starting conditions are changed in ways that break other parts of the model. Another suggestion is that this could be a topological feature, a result of the way space itself is shaped. If space-time curves or loops at extreme scales, it might produce mirrored or repeating patterns. But again, this would imply a radical departure from what current data supports. Some astronomers proposed a link to primordial gravitational waves, ripples from the early universe that could have seeded unusually shaped structures. But the pattern would need to be incredibly specific, and we've never observed anything else like it elsewhere in the sky. Then there's the even stranger possibility that we're seeing the edge of something. Not the universe itself, but the boundary of a different causal domain, a region of space that evolved slightly differently due to quantum fluctuations after inflation. In such a case, the giant arc might not be a structure in our universe, but a pattern caused by a gradient or shift in physical laws from one region to another. Still, there's no proof that the physics in this area are different. No strange action from particles. There are no gravity oddities, only the arc. Another time this kind of building has caused trouble is not long ago. Astronomers had already found the Hercules Corona Borealis Great Wall many years before. It is another huge group of galaxies that spans more than 10 billion light-years. That also put the cosmological principle to the test. The giant arc, on the other hand, feels different. better. Smoother in terms of geometry. It looks less like a cosmic wall and more like a line drawn on the sky. Could it be the result of a gravitational lensing illusion? That would require a foreground mass large enough to bend space in just the right way. Not impossible, but highly unlikely at this scale. And again, no such lens has been found in that region. In the end, the giant arc remains one of the best examples of observational astronomy challenging theoretical cosmology. It's there, it's real, and it's weird. Researchers are now focusing new instruments, including radio and X-ray telescopes, on the arc to gather more data about the galaxies involved. Are they interacting? Are their ages synchronized? Do they share star formation rates or chemical compositions? Because if they do, it's even more mysterious. Not just that they're grouped in an arc, but also that they were all born as part of the same big plan. One thing is for sure, the world is still full of shocks. It could be a trick of the eye, a flaw in the model, or the way physics works that we don't fully understand yet. This kind of surprise can take the form of a perfect cosmic curve. The accelerating expansion that shouldn't be possible. Beginning in the late 1990s, two groups of scientists set out to find out how fast the universe was rising. They thought that gravity would have slowed the spread that started with the Big Bang over time. Instead, they found something so shocking that it changed the way we think about the world today. It's not just growing, it's speeding up. It's not that galaxies are sliding farther apart, they're actually moving farther apart faster and faster. The findings came from studying Type Ia supernovae, a specific kind of exploding star that always reaches the same peak brightness. These supernovae act like cosmic mile markers, standard candles that let scientists measure vast distances. But when they looked out at supernovae billions of light years away, they were dimmer than they should have been. That meant they were farther away than expected. And the only explanation was that space itself had expanded more than anticipated, pushed outward by a mysterious force. This force was dubbed dark energy, a term that's basically a placeholder for "we have no idea what this is." The equations of general relativity don't naturally predict accelerated expansion. In fact, when Einstein first developed them, he added a term called the cosmological constant to keep the universe static, because that's what everyone believed at the time. He later called it his greatest blunder. But now, that same constant, or something like it, might be responsible for this runaway expansion. Scientists tried to calculate how much energy would be required to push the universe apart like this. Using quantum field theory, they came up with a number. Unfortunately, that number was 120 orders of magnitude too large. Not slightly off, absurdly, catastrophically wrong. That's like predicting Mount Everest will be 1,000 light years tall tomorrow. It's the most inaccurate prediction in the history of physics. One idea is that dark energy is a property of space itself. Every cubic centimeter of space, even the empty vacuum between galaxies, holds a tiny amount of energy. And as space expands, more of it is created, bringing more dark energy with it. The more space there is, the faster it expands. It's a runaway loop with no known end. Recent measurements using different methods, such as studying the cosmic microwave background with the Planck satellite, and measuring local galaxy motion with the Hubble Space Telescope, have produced different values for the universe's expansion rate, known as the Hubble constant. The Planck results point to a growth rate that is slower. Hubble says it's going faster. The numbers are not coming together, they are moving apart. We have a problem with that. This difference is now called the Hubble strain, and it's making scientists think that our whole model of the universe might need to be changed. Dark energy might not always be there. It could change over time. We might be missing a piece of the puzzle, like an unknown particle, a new force, or even a mistake in how we think about gravity. Another theory proposes quintessence, a dynamic form of dark energy that changes in strength over time, unlike the fixed cosmological constant. But so far, there's no direct evidence for it. Others suggest the expansion might be anisotropic, not the same in all directions. If true, that would shatter the foundational assumption that the universe is homogeneous on large scales. We've even considered that the observed acceleration might be a mirage caused by our position in a large cosmic void. But surveys of galaxy distributions don't support this. We're not in a special place. The acceleration is real. Things are breaking apart faster than they should. The reason is hard to see, hard to measure, and hard to understand. The amounts don't match up. The ideas don't fit together. And the models, which are our most important mathematical plans, are breaking because of all the new information. However, this is where astronomy stands right now. Something is moving worlds apart. That much we know. It changes all the time, and we have no idea what it is or how it works. NASA's upcoming Nancy Grace Roman Space Telescope, along with ESA's Euclid mission, are both designed to probe dark energy more deeply. They'll map billions of galaxies, measure the growth of cosmic structures, and hopefully shed light on this accelerating mystery. The signal from galaxy SDSSJ 1429 plus 5447. Astronomers found a strange signal coming from a galaxy called SDSSJ 1429 plus 5447 in 2022. This galaxy is so far away that it took billions of years for its light to reach us. At first, it looked like the discovery was just another blip in the background noise of space. This was not normal communication, though. It was repeating, narrowband, and shockingly structured, which are all things that are very rare in the natural world. Most radio emissions from galaxies are broad spectrum and chaotic. Noise from black holes, star formation, or galactic magnetic fields. But this one came through in a very specific frequency band, much like how a radio station broadcasts on a precise number. That alone raised eyebrows. Then came the repeating pattern. The signal pulsed in intervals that didn't match any known astronomical object. Not a pulsar, not a quasar, and not the usual fast radio burst, FRB, suspects either. Even more unnerving, the signal displayed frequency drift, changing pitch over time, as if something was intentionally modulating it. Now, we've seen FRBs before, fast radio bursts that flash for milliseconds from deep space. Some repeat, most don't. But this one didn't behave like a traditional FRB. It wasn't just short, it was clean, like a signal designed to stand out against cosmic static. What made it even stranger was its source. SDSSJ 1429 plus 5447 isn't a particularly remarkable galaxy. It's not known to house an active galactic nucleus, nor is it a starburst galaxy churning out extreme radiation. It sits in a fairly uninteresting part of the sky, which makes the signal all the more baffling. The first hypothesis, some kind of magnetar activity. Magnetars, ultramagnetic neutron stars, are known to produce brief bursts of radio waves, but magnetar emissions usually come with X-ray or gamma-ray signatures. In this case, none were found. No high-energy companions, just the radio pulse, alone and unexplained. A second possibility was gravitational lensing, that something massive between us and the galaxy distorted another signal into this precise shape. But again, no evidence of such a lens was found in follow-up observations. The signal wasn't bent, magnified, or duplicated. It came straight from the galaxy, as far as we could tell. Then, the wildcard idea called technosignature came along. A technosignature is any proof that can be found of advanced technology, which is often linked to the idea of alien intelligence, a narrowband sound that keeps repeating and changes frequency. That's exactly the kind of message SETI researchers hope to find. It sounds like how we might send a sign through space. It's simple, repeats itself, and is tuned to stand out from background noise. That being said, this doesn't mean aliens. This means we don't understand what's going on. And when science can't put something into a group, it looks at it very closely. Researchers attempted to replicate the detection using other radio telescopes, including CHIME in Canada and the Meerkat Array in South Africa. Some confirmed elements of the signal, others didn't. The source remained inconsistent, flaring on some days, silent on others. It was as if the signal had a schedule, one we hadn't cracked yet. This sparked a broader debate about how many strange signals we've overlooked. Modern sky surveys generate petabytes of data, far too much for humans to sift through. Many detections get flagged and discarded because they don't fit known patterns. But what if the patterns we're ignoring are the ones we should be investigating most? We have been watching for months, but we still don't know what the signal is. We have no idea how it's made. It's possible that it's still turned on. It flickers behind a mist we can't lift, coming and going. It doesn't act like a magnetar should. There isn't enough chaos for a chance flare. Also, the theories for regular FRBs, gamma-ray bursts, or active galactic nuclei don't work with it. There are no more hints from the galaxy itself, no flares, no high-energy releases, and nothing else that points to extreme activity. We might be seeing a new kind of cosmic event, something that doesn't fit into any of the categories we use now. To make things even more interesting, it could be a fake signal sent by processes or intelligences we haven't figured out yet. A magnetic field that shouldn't exist in deep intergalactic space. The farther out you go in space, the easier it should be, right? The universe is expected to get quieter, darker, and emptier as you move past galaxies, clusters, and cosmic strands. But in 2010, astrophysicists using data from the Fermi Gamma-Ray Space Telescope found something that went against what was thought to be possible. A magnetic field in intergalactic space, which is very far from stars, planets, and anything else that should be able to make it. And not just a weak magnetic field either. This one spanned millions of light years, covering enormous stretches of voids between galaxies, regions previously thought to be magnetically neutral. The magnetic field wasn't uniform, but it was coherent, suggesting it had structure and direction. In a place where nothing should be, something invisible was shaping particles and bending space. Researchers were studying blazars, supermassive black holes that emit intense beams of gamma radiation. As these gamma rays move through space, they collide with the cosmic microwave background, CMB, producing electron-positron pairs. These charged particles, in turn, should create a cascade of lower-energy gamma rays, forming a sort of afterglow that telescopes like Fermi can detect. But there was no glow. It's not like the secondary gamma rays were there. It looked like the particles were being pushed or redirected before they could finish their trip. The only theory that makes sense. The charged particles were being pushed off course by a magnetic field in the intergalactic medium. This spread the beam out across space and made it thinner before it reached Earth. The presence of a magnetic field wasn't the strange part. What shocked scientists was where it was and how large it had to be to cause this effect. Intergalactic magnetic fields were theorized, yes, but they were expected to be faint, patchy, and caused by galactic winds or relics of supernovae, not sprawling, organized structures stretching across voids. Where did this field come from? One theory is that it's primal, meaning it's something that was there right after the Big Bang. Some ideas say that quantum fluctuations in the early universe might have created very small magnetic seeds. These seeds were then stretched and magnified as space expanded over billions of years. But if that's true, this would be one of the oldest and biggest magnetic fields ever seen. It would be like seeing a ghost from the beginning of time. Another idea is that it's generated by galactic outflows, winds from star-forming galaxies that blow magnetic fields into the surrounding void. But the strength and uniformity of the field don't match this model. For such a massive region to be magnetized, the energy required would be enormous, far more than what known galaxies could reasonably provide. This leads to a more speculative concept, cosmic strings, or other exotic relics from early universe physics. These hypothetical structures could, in theory, warp spacetime and induce large-scale magnetic fields, but we've never seen direct evidence of such objects. The fact that the magnetic field stays the same in different gaps adds to the puzzle. It looks like it's all over the world, not just in one place. It is weak, but it is definitely there. That regularity points to a deep global beginning that doesn't depend on matter or energy as we know them. Because we're missing a big part of our understanding of how the universe evolved if these magnetic fields are essential to space itself. They might have had an effect on how galaxies formed, how cosmic strands moved, and even how dark matter was distributed. To sum up, we might have missed an invisible support framework that shapes the structure of the world. To test this, scientists are turning to next-gen telescopes like the Square Kilometre Array, SKA, and CMB-S4, which will have the sensitivity to map faint magnetic imprints across the cosmos. These observations might reveal not only the strength and orientation of intergalactic fields, but their origins, whether they're ancient, galactic, or something else entirely. Unexplained gamma bursts with no known source. Gamma-ray bursts, or GRBs, are some of the strangest and most powerful events in the world. They are brighter than whole galaxies, even if only for a few seconds, and they usually come from terrible things happening in space, like a huge star collapsing or neutron stars merging. We have a list of hundreds of them. They normally leave behind afterglows in X-ray, visual and radio waves that help us figure out where they came from. But once in a while, a burst of gamma rays shoots through the space, and nothing is left behind. These are the unexplained GRBs, flashes of intense energy with no origin, no afterglow, and no trace. They appear suddenly with no precursor and vanish without explanation. 1 second, the sky is silent. Next, it lights up with radiation so powerful it would fry electronics from light years away. And then, nothing. The most perplexing examples come from instruments like the Fermi Gamma Ray Space Telescope and Swift Observatory, which are designed to detect high-energy cosmic events. In several cases, these satellites recorded short gamma-ray bursts, lasting less than 2 seconds, with no matching X-ray or optical signature, and no known galaxy or celestial body at the location. One particularly strange burst, known as GRB 070201, was detected near the Andromeda Galaxy in 2007. It lasted only 0.15 seconds, but released more energy than our Sun will emit in its entire lifetime. Naturally, astronomers expected to find some kind of aftermath: a fading glow, a dying star, a gravitational wave signal, but nothing followed. No visible light, no radio echo, no debris. It was as if the burst came from nowhere. What's even stranger is that the event happened so close that we should have seen something. But it was dark in the field. Some scientists thought it might not have come from a star falling, but from something even stranger, like a soft gamma repeater in our local group, or a primordial black hole disappearing through Hawking radiation. But those thoughts also didn't last. Most of the time, soft gamma repeaters repeat. No, this one didn't. Also, Hawking radiation is just a theory. It is much weaker than what has been seen. That left us with a space flashbulb and no camera. One single flash of light that was very powerful. Another category of these mysterious events is known as dark GRBs. They're not literally dark, but they lack optical afterglows, which makes them difficult to localize. Some might be hiding behind clouds of dust, absorbing visible light. But others occur in regions with no dust, no gas, and no host galaxy nearby. These naked bursts leave astronomers scratching their heads. How can something so powerful come from a place that appears completely empty? Some unexplained gamma bursts show spectral properties that don't match any known mechanism. The shape and timing of the emission curve don't align with neutron star collisions or black hole accretion. They don't even mimic the patterns we see in magnetars or active galactic nuclei. In one case, the burst, identified as GRB 200415A, lasted just 140 milliseconds, but the gamma-ray flux was so intense it saturated instruments. The burst came from a magnetar in our galaxy, but its intensity and clean, isolated signal didn't match expectations. Scientists still argue over whether it was a one-off flare or something more fundamental. There's also the scary chance that we're seeing something completely new, a type of cosmic event we don't know anything about. A black hole has a hiccup, a particle collision at very large sizes. A cosmic string snapping is a made-up artifact from the early universe that, if broken, could release huge amounts of energy. Some fringe theorists have even proposed techno-signatures, bursts of energy from alien civilizations performing astrophysical scale engineering. While that's not the mainstream view, the absence of any physical source keeps the door cracked open. NASA and ESA are preparing next-generation gamma-ray detectors like Amigo X and Theseus, which aim to localize these mysterious bursts more precisely. The hope is that with higher resolution and faster response times, we'll catch one of these anomalies in action and finally trace it back to its source. Until then, we wait. A void in the universe so big it breaks the models. You expect to find empty spots in space where there aren't as many stars, galaxies, or objects. But in 2007, scientists found a place that was so empty and barren that it didn't fit any of our models of the universe. It wasn't just a space. It was the supervoid, a huge dark space in the universe that was almost 1.8 billion light-years across. Plus, we still don't understand how it works. Let's put that size into perspective. The Milky Way galaxy is about 100,000 light-years wide. So this void could fit 18,000 Milky Ways end to end and still have room to spare. It's located in the constellation Eridanus, which is already home to another cosmic anomaly, the cold spot in the cosmic microwave background, CMB. At first, scientists assumed these were unrelated, but the more we looked, the weirder it got. The cold spot was first detected by the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite. It showed a region in the CMB, the afterglow of the Big Bang, that was noticeably cooler than its surroundings. This alone was strange, since the early universe should have smoothed out such temperature differences over billions of years. But when researchers pointed radio telescopes at that same spot in Eridanus, they realized something else. There were far fewer galaxies in that direction. The density of galaxies dropped by up to 20% compared to similar patches of sky. And it wasn't a local dip. This void stretches across hundreds of millions of parsecs, both wide and deep. It isn't just a gap, it's a scar, a wound in the fabric of the universe that current physics can't explain. Now, voids aren't rare. The universe is structured like a cosmic web. Galaxies cluster along filaments with empty spaces in between. These are normal. But the Eridanus supervoid is too big, too empty, and too cold to be brushed off. According to our best simulations of cosmic evolution, such a structure shouldn't exist in the observable universe. So what's making it happen? It's possible that this supervoid is just a statistical blip in a very big set of data. Most models, though, say that the chances of such a gap appearing naturally are less than 1 in 50,000. The integrated Sachs-Wolf effect is another idea. This effect says that photons from the CMB lose energy as they move through big holes or wells of gravity. It's possible that this could explain the cold spot. But the amount of energy lost doesn't fully match what has been seen. Others have suggested it could be a sign of non-standard inflation, meaning the early universe may have expanded in ways that vary by region, causing uneven temperature and density profiles. But this theory threatens to unravel the whole idea of cosmic homogeneity, the principle that the universe looks roughly the same everywhere on large scales. Could the gap be the mark of a bubble universe? A place where different physical rules applied that brushed up against our own universe right after the Big Bang? This idea of a cosmic bruise is debatable, but it seems to fit. You might see scars like these if our universe is part of a bigger multiverse, and bubble worlds sometimes crash into each other. Cool places. There are dead zones. There is proof of effect. Of course, this is still just a guess. There is no clear proof that there are other worlds, and most physicists still think of the multiverse as a theory that hasn't been proven. But when it comes to strange things like the Eridanus supervoid, people's imaginations tend to take over when facts fail. The fact that this void doesn't seem to be moving nearby galaxies in a big way adds to the puzzle. If an area this big was really less dense, it should have effects on gravity. But the galaxies around it aren't acting strangely so far. It seems like this empty space is always there, huge, still, and uninterested. Radio arrays and infrared cameras are still doing new scans to figure out how big it is. And new projects like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope may help make things clearer. The cosmic web filaments that pulse for no reason. If scientists take a big picture, look at the universe, they don't just see a bunch of galaxies here and there. Instead, they see structure, the cosmic web, a huge web of matter that is all linked to each other. These filaments are huge threads of dark matter and gas that connect galaxies and clusters like roads on a huge map of the galaxy. They stretch over hundreds of millions of light years. The universe is held together by these threads. But lately, someone has seen something strange. Some of these huge strands don't just sit there in a straight line. They beat. Yes, pulse means to shine, change in energy, or act in slightly rhythmic ways every so often. No one understands the reason. The discovery came from a combination of observations using radio telescopes and X-ray surveys. Astronomers noticed that certain filaments, particularly those connecting galaxy clusters, were showing time-variable emissions. That's weird enough, but it gets stranger. These emissions weren't tied to any specific event like supernovae or black hole activity. They seem to fluctuate with no local cause. One of the most studied examples is a filament connecting the Able 222 and Able 223 galaxy clusters. Researchers detected a bridge of X-ray emitting gas between the two clusters. That was expected, hot gas trapped by gravity. But over time, the brightness of this bridge subtly changed. At first, scientists thought it might be due to intervening objects or data error, but repeated measurements showed a real, rhythmic variation in intensity. Imagine a building hundreds of millions of light years long that slowly changes its brightness for no clear reason. Some scientists think that these pulses might be caused by shock waves, which are huge bursts of energy that happen when galaxies or dark matter collapse. But that still doesn't fully explain why the changes happen at the same time or over and over again. In some places, the gaps are too consistent, almost like the beat of a heart. But space doesn't have a heart, does it? Another theory suggests the involvement of magnetic reconnection, the same process that causes solar flares on the Sun. If magnetic fields in these filaments twist and snap back into place, they could release bursts of energy. But to apply that mechanism across a structure spanning millions of light years requires a scale of magnetic influence we've never observed before. There is also the chance that dark matter is doing something we don't know about. We know that dark matter gives these strands their shape. It doesn't give off light, but it has a lot of pressure. It's possible that dark matter can engage with itself in strange ways. If that's the case, it could be sending out small density waves that heat up or squeeze the gas stuck in these cosmic bridges, which is what we see as pulses. But for this to work, dark matter would have to have qualities that aren't in current models. This could mean that dark matter interacts with itself, or even that dark plasma exists. Similar waves have been seen in studies of the cosmic microwave background, which makes the puzzle even more difficult to solve. Light from galaxies far away bends around these strands in slightly different ways at different times. Again, these are small effects that have been seen in many studies. It feels like the very fabric of space is moving. Could it be a problem with the instruments? It's not likely at this point. Signals that match have been found by separate studies using very different telescopes, such as the Rosetta, LOFAR, and South Pole telescope. Even though the trends aren't very interesting, they keep happening. Some researchers have floated more speculative ideas, that these pulses might be caused by axion-like particles, or that they're evidence of unknown interactions in the early universe echoing through time. Others consider more exotic theories, like the cosmic web itself oscillating as part of a larger physical framework we haven't yet uncovered. And yet, these quiet pulses continue, measured in slight shifts of X-ray flux, in anomalies in gravitational lensing, in unexplained heat signatures drifting across the void. They remind us that even the most colossal structures in the cosmos may not be as static as they seem, that even in the great silence of intergalactic space, something is moving, something is alive. Saturn's hexagon and its possible link to deep space waves. Astronomers have always been interested in Saturn, the gas giant with the famous rings. But one of the weirdest things about it isn't its rings, it's a shape. At its north pole, the clouds have carved a perfect, huge hexagon. This geometric storm system was found by the Voyager spacecraft in the 1980s and later seen in high definition by the Cassini spacecraft. It covers almost 14,500 kilometers, which is longer than Earth, and spins in a strangely stable way. In addition to having been there for decades, the hexagon may have something to do with wave or gravity patterns in deep space, which would have effects far beyond Saturn itself. The hexagon is made up of six-sided jet streams that are made up of fast winds going about 320 kilometers per hour. It shapes a nearly perfect polygon with straight sides and sharp corners, which is different from any other planetary storm system in our solar system. A lot of weather systems are messy, unsteady, and full of chaos. But Saturn's hexagon is exact and doesn't move. It's a steady, rhythmic trait that goes against what the atmosphere should be like. The data from Cassini showed something even scarier. The hexagon's spin is the same as Saturn's radio emission period, which was once used to figure out how fast the planet was rotating inside. Because of this, some people think that Saturn's core, magnetic field, and upper atmosphere may all be linked in a deeper way that isn't just about planetary weather. Scientists found strange resonances when they compared the oscillation patterns in Saturn's atmosphere with data from faraway gravity waves and ripples in the cosmic background. Gravitational waves from black hole mergers aren't said to be changing Saturn's clouds. That's just an idea. But it was suggested that Saturn's atmosphere, with its low density and fast spin, might act as a natural resonator, boosting very low-frequency cosmic signals. What if the triangle on Saturn is a space antenna? It's a crazy idea, but it's not completely ruled out either. Some theoretical scientists think that planets like Saturn might be able to sense changes in scalar or gravity fields coming from far away because of their large gas envelopes and magnetic fields. These might not be directly measurable by our tools, but they could have a small effect on fluid dynamics, especially over long periods of time. A lot of people became interested in this idea after LIGO started finding gravitational waves in 2015. Researchers were interested in whether any slow background waves that can't be found with the tools we have now could still have physical effects on huge things that are spinning. We can't prove this yet, of course. But some strange things make the puzzle even bigger. As an example, Saturn's north pole has a hexagon shape, while its south pole has a huge swirl that doesn't have any physical shape. Why would this strange behavior only happen on one pole? Some people think that outside forces, like being in line with the circular path of the solar system, or being exposed to cosmic flows from above the galactic plane, may have an effect on the upper atmosphere that we don't fully understand. During seasonal changes on Saturn, color shifts inside the hexagon were observed by Cassini. Ultraviolet light exposure seemed to alter the chemical composition within the storm, which is expected. But the rate and symmetry of those shifts were more consistent than models predicted, hinting again at some deeper, stable rhythm beneath the surface. If there's a broader connection to deep space, it may lie in Saturn's resonance with the Sun and other planets. Orbital resonances are common in our solar system. Jupiter and Saturn influence each other's orbits, as do Neptune and Pluto. But what if those gravitational relationships extend vertically as well, beyond the ecliptic plane? What if cosmic currents, not just gravitational pulls from neighboring planets, play a role in shaping the atmospheric features we see? Some researchers have gone as far as linking the hexagon to standing wave patterns, like those seen in fluids on Earth when vibrated at certain frequencies. If the gas giants float in a gravitational bath, it's not impossible that stable, long-lived wave patterns could emerge. Saturn, with its ideal rotational speed, density, and atmospheric composition, might just be the perfect canvas for such cosmic interference. There is, of course, a much easier way to explain it. Saturn's hexagon could be a natural result of how fluids move. Similar polygonal flows have been produced in the lab using spinning spheres and liquids with different densities. But none of those models have been able to make a six-sided storm that lasts as long, is as big, and is symmetrical as Saturn's. Dark energy readings that change over time. Dark energy is an imaginary force that seems to be pulling the universe apart faster and faster. It has been the most mysterious force in astronomy for decades. It can't be seen. Matter has nothing to do with it. But based on existing models, it makes up about 68% of all the energy in the universe. Scientists found dark energy by looking at Type Ia supernovae, which are faraway explosions of stars that serve as cosmic mile markers. To everyone's surprise, they seemed fainter than expected, which meant the universe wasn't just growing, it was speeding up. This revelation shattered long-held assumptions. Scientists had assumed gravity would slow cosmic expansion over time. Instead, something was making the universe speed up. Enter dark energy, an unknown form of energy with negative pressure, spread evenly throughout space. Dark energy keeps changing no matter how much we look at it, that it might be changing. Lambda CDM is the standard model that says dark energy is a cosmological constant, which means it has a set energy level that doesn't change in space or time. But new studies from the Planck, Euclid, and Hubble space telescopes show that might not be the whole story. Some findings suggest that dark energy's effect was less strong in the past and is getting stronger as the universe ages. Dark energy's behavior is often described using a number called W, the equation of state parameter. If W equals sign -1, dark energy is a perfect cosmological constant. But if W deviates from -1, even slightly, it could mean dark energy changes over time. And recent surveys of supernovae and baryon acoustic oscillations, ripples in the large-scale structure of the universe, suggest W might be closer to -0.95 or even -0.9 at certain epochs. That deviation could mean dark energy is not a fixed field but something dynamic. Maybe it's a scalar field, like quintessence, that changes slowly over time. Or maybe it's tied to exotic particles we haven't discovered yet. Either way, the constant may not be constant. What does this mean? Dark energy changes things, so the fate of the universe changes too. A heat death, or a slow fading as galaxies move apart, is what the standard model says will happen. But if dark energy gets stronger, the universe might end in a big rip. In this event, the universe expands so quickly that it breaks galaxies, solar systems, planets, and even atoms apart. This terrible thing that could happen tens of billions of years from now. But even that relies on how stable dark energy stays. In some regions of space, particularly in voids, dark energy density seems to behave differently. A study from the Dark Energy Survey, DES, found subtle differences in expansion rates depending on location. These variations are still under review, but they raise a disturbing possibility. Dark energy may not be uniform. It may fluctuate, or be influenced by local matter density, or even have phase transitions, similar to how water can exist as vapor, liquid, or ice. If this is proven to be true, it would destroy the idea of an isotropic universe, which means that the universe looks the same from every angle. This would require scientists to start from scratch in order to understand how the universe is put together. Some researchers have found even stranger links between dark energy and entropic forces, string theory fields, or even information theory. These links suggest that dark energy may be connected to the very structure of spacetime, or be a result of entropy balancing itself across the universe. Despite its dominant presence, we can't detect dark energy directly. It leaves no spectral lines, no mass signature, no particle trail. Its fingerprints are only visible in the motion of galaxies and the stretching of light. That makes it not just strange, but dangerously untestable, at least with current instruments. The Nancy Grace Roman Space Telescope, which is set to launch in the next few years, will look into dark energy with a level of accuracy that has never been seen before. It will try to figure out how we change over time and space by making maps of billions of galaxies and supernova. And maybe, just maybe, it will tell us if the force speeding up the universe is a quiet whisper or a rising scream. A rogue planet with no star, emitting radio signals. We usually think of planets as loyal partners to stars, stuck in circles and held together by gravity and light. But some worlds don't follow the rules. Some people wander around by themselves. Rogue planets are big, cold worlds that are floating through space without a star. Another one was found in 2016 that did something that no one thought a rogue planet would do. Radio waves came from it. The object, known as SIMP J013656663 plus 0933473, or just SIMP for short, is a planetary mass body located about 20 light-years from Earth. It was discovered as part of a survey looking for failed stars called brown dwarfs, objects too large to be planets but too small to sustain fusion. But SIMP defied categorization. It was originally classified as a brown dwarf. Then, with more refined data, scientists realized it was only about 12.7 times the mass of Jupiter, right at the boundary between a planet and a star. Using the Very Large Array, VLA, in New Mexico, researchers detected strong radio emissions coming from SIMP, emissions that resembled the auroras we see on planets like Jupiter, but much more powerful. We're talking about radio bursts in the gigahertz range, far stronger than any planet is supposed to be able to produce without a host star's energy driving its magnetosphere. A cold, starless world that is floating through space and giving off radio waves. There is only electricity and wonder, no sun or moon. So what's making it happen? SIMP has a magnetic field that is over 200 times bigger than Jupiter's. This is the most likely answer. If the planet has a moon or ring system that interacts with the field, that is enough to make the aurora happen on a big scale. Some scientists think that SIMP's strong radio bursts could be caused by a huge exomoon circling and setting off magnetic interactions in the same way that Jupiter's moon Io causes its auroras. It's just that we haven't seen such a moon yet. There is no sign of one in the visible or infrared spectrum, but the radio flashes keep coming. It seems like SIMP is running on its own power. Some scientists think that rogue planets like SIMP may still have heat inside them from when they were formed, which could keep oceans or hot cores alive for billions of years. That heat, along with metallic hydrogen deep inside, could make a strong planetary dynamo. This would be like how Earth's iron core makes its magnetic field, but on a much larger scale. This might explain the magnetic power of SIMP, but not the fact that its signs come at regular times. What's really strange about SIMP is that its radio output changes over time and rotates like a pulsar. It's like the Earth has a radio energy beam that goes across the sky like a lantern. That's not how planets usually work. It's how neutron stars and other strange leftovers work. This led to thoughts on the edge. Some experts have thought that SIMP might not even be a planet, but a new type of object called a planetary mass radio emission, whose power source is still unknown. Could it be reacting with the space between the stars in a strange way? Could its magnetic field be hitting charged particles in space, which would keep the aurora going in a way we've never seen before? Then there's the wildest theory. What if some rogue planets carry remnant stellar cores, left over from failed binary systems, or possess dark matter interactions that somehow contribute to sustained energy output? No solid evidence supports this, but the fact that SIMP doesn't fit our neat little boxes leaves the door cracked open. Since the discovery of SIMP's emissions, astronomers have started pointing their radio arrays at other rogue objects. A handful now appear to show similar, if weaker, radio traits. This raises the possibility that radio-loud rogue planets are more common than we thought, and we've simply been blind to them until now. If rogue planets can emit detectable radio waves, they could be accidentally masquerading as other celestial sources in deep space scans. That mystery blip in a survey? It might not be a distant galaxy or a supernova remnant. It might be a planet, quietly howling as it drifts between the stars. More practically, this opens a new method for detecting free-floating planets. Traditionally, we find them via gravitational microlensing, a difficult and rare event. But if we can start identifying rogue planets by their radio signatures, it could vastly expand our knowledge of planetary systems beyond stars. X-ray jets from the middle of nowhere. There are many jets in the universe. We see them coming out of black holes, new stars and galaxies that are powered by giant engines. These jets, which are usually made up of very high-energy particles, shoot out in orderly columns and move at almost the speed of light over unimaginable distances. X-rays, gamma rays, and radio waves can make them light up. However, every known plane has a source. One exception. Astronomers found a single X-ray jet in a part of deep space. A beam of high-energy radiation that seems to appear out of nowhere and is about 1 million light-years long. NASA's Chandra X-ray Observatory was the first to see this event. This is a satellite that is meant to find some of the most energetic and faraway things in the universe. The jet was weak but clear. It pointed in a single direction like a cosmic arrow, and its shape was strangely clear. It acted like a normal AGN jet, but you couldn't see what its dad was. That's like seeing a smoke path, but no fire. There is no chimney, not a building. It's just smoke floating in the air with no source. Astronomers, of course, rushed to figure out what was going on. Some people thought the jet might have come from a quasar or black hole that has since changed its brightness or moved out of view. But even if the source went away, we should still be able to see signs of it, like a faint galaxy, an infrared signal, or gravity structure that is still there. There is only cosmic emptiness instead. Another theory? The black hole that launched the jet might have been ejected from its host galaxy due to a gravitational interaction, such as a black hole merger recoil, where two massive black holes combine and kick the final product out of the galactic core. If true, the black hole could now be flying solo through space, dragging its ancient jet like a flag behind it. But there's another catch. The black hole is also gone. Not many big groups. There is no radiation. There was no change in the light in the background, only the beam. The universe shot an arrow and then erased the shooter. This discovery has baffled scientists because the jet's properties match those from known sources. The structure suggests it is powered by relativistic particles, accelerated along a magnetic field, textbook black hole physics. Yet, the very existence of this jet violates that textbook by lacking the engine. Some people think the jet isn't coming from a black hole at all, but from an unknown type of cosmic engine that doesn't give off light or gravity pull in the usual ways. This might be a dark matter object, but not a clump. It might be something moving that only gives off radiation in strange situations. Or is the jet something that is left over, like an artifact from before galaxies? To test these ideas, scientists turned to multi-wavelength surveys, hoping to catch any supporting clues in infrared, optical, or radio frequencies. Nothing turned up. The jet remains a ghost, detectable only in X-rays. The building itself is strange. There is no turbulence, knots, or flare in this jet like there is in other planes. The same. It has been in space for millions or even hundreds of millions of years and has kept its shape. That means the starting point has a lot of energy and is very steady, no matter where it is. Some researchers tried to use gravitational lensing models to account for the odd location. Maybe the jet appears displaced because of warped space-time from a massive object in the foreground. But this too fell apart. Lensing would have bent the jet's light, but not eliminated the source. The problem isn't distortion, it's absence. And there were people who really believed that the jet could have been an echo, like a light trail from something that fell into a higher dimension or went through a wormhole. It's only a guess what these ideas are, since there's no real evidence to back them up. Jets are thought to be caused by giant processes, but this one doesn't have any mass nearby. This could mean that we're missing a whole class of unseen cosmic engines, or we don't fully understand it yet. The galaxy that appears to have no dark matter. Dark matter holds the world together, but we can't see it. It doesn't give off light or radiation, and electromagnetic forces can't affect normal matter. But galaxies shouldn't exist without it. Models and simulations that have been running for decades say that the gravity of stars, gas, and dust isn't enough to keep galaxies together. As they spin, they should fly apart. Dark matter's extra mass holds everything together, even though it can't be seen. Every galaxy we know of needs it. One exception. Astronomers using the Dragonfly telephoto array reported in 2018 that they had found a galaxy called NGC 1052 DF2. It is made up of a faint, spread-out group of stars that are floating about 65 million light-years away. From far away, it didn't look like anything special. But when scientists looked at how it moved, they saw something amazing. There wasn't enough speed in the stars. There was no dark matter at all, so the galaxy's internal speeds were exactly what you'd expect. That's surely not enough. That's nothing. The implications were immediate and massive. If NGC 1052 DF2 truly lacks dark matter, it overturns a major assumption. That dark matter is essential for galaxy formation. It also suggests that galaxies can somehow form and stay stable using only their ordinary matter. Normally, astronomers measure a galaxy's mass by observing how fast stars orbit the center. The faster they orbit, the more unseen mass must be pulling them in. But DF2's stars moved slowly, so slowly in fact, that their combined motion could be explained entirely by the visible matter alone. This wasn't a simple math mistake. The numbers showed that DF2 had 400 times less dark matter than was expected. If it's true, this wasn't just a strange case, it was a glitch in space. The critics fought back. It's possible that the distance guess was off, since DF2 might look like it doesn't have dark matter when it doesn't, if it were closer than we thought. But later views by the Hubble Space Telescope and the Keck Observatory confirmed the distance and backed up what had been found before. Researchers found a second galaxy, DF4, in the same area. It had almost no dark matter, just like the first galaxy. That turned a coincidence into a trend. There were two galaxies floating in the same area of space. They were both clear and ghostly, but they were held together without the stuff we thought held galaxies together. What's going on here then? One idea is that DF2 formed in a very rough place, close to the huge elliptical galaxy NGC 1052. A dark matter halo that used to circle DF2 may have been torn away by gravity forces or tidal stripping. Only stars and gas are thought to be left behind. But if that's the case, it's not clear how the rest of the matter stayed stuck together by gravity. Another idea flips the story. Maybe DF2 never had dark matter at all. Maybe it formed from gas ejected during galaxy collisions or extreme cosmic winds, forming a tidal dwarf galaxy. These are rare, but not impossible. In such a scenario, DF2 could have coalesced entirely from normal matter, avoiding dark matter altogether. Dark matter is important and can be found everywhere. So how did this galaxy get missed? What kinds of conditions must be present for a galaxy to form before it can use the cosmic dark matter reservoir? Even scarier, DF2's globular clusters, which are dense groups of stars, are very bright and heavy for their size. Some experts think this could be a sign of new gravitational physics or unusual feedback processes. Others aren't sure if we're seeing a new type of galaxy, one that only forms in very specific, not well understood circumstances. This galaxy, barely visible through the black, is whispering something uncomfortable. Maybe our map of the universe is missing some streets, or maybe our assumptions about dark matter are flawed. The repeating FRBs that shift frequencies over time. Fast radio bursts, or FRBs, are one of the strangest and least expected things that can happen in modern science. These are very short bursts of radio waves that come from outside our galaxy. They last only milliseconds, they move quickly, they're smart, and until recently, no one thought anything about them. But in 2020, scientists saw something that changed everything. Scientists were shocked when one FRB, called FRB 121102, started to act in a strange way. It wasn't just repeating, which was strange enough. The frequencies were also changing in a way that no known physical process could fully explain. It wasn't silent bursts. They were getting better, changes. It's kind of like a coded signal going through different radio stations over time. Let's start with what we know. FRB 121102 is located over 3 billion light-years from Earth. That means whatever is causing these bursts must be incredibly powerful, emitting more energy in a single blink than our Sun releases in an entire day. Most FRBs are one-and-done events, detected once and never again. But 121102 became the first fast radio burst to repeat. At first, the bursts came irregularly. Then a rhythm emerged. Researchers noticed that the bursts followed a 157-day cycle, 90 days of silence, followed by a 67-day period of active bursts. Not only did the signal repeat, but during each active window, the bursts themselves showed a shift in frequency, almost like a descending tone from one burst to the next. This frequency drift was steep, not just subtle changes, but sharp, rapid steps, something akin to a radio broadcast being manually retuned during each transmission. Known astrophysical objects that can emit radio waves, like pulsars or magnetars, typically operate on consistent frequencies based on their spin or magnetic field strength. So the fact that 121102 is both shifting its frequency and doing so in predictable patterns doesn't match up with any known mechanism. Theories poured in. One proposed explanation was that the source is orbiting another object, perhaps a black hole, and the gravitational interaction causes the signal to bend or shift over time. That might account for some variation, but not the clear downward drift in frequency over such short timescales. Another theory looked at plasma lensing. Maybe the signal is passing through a dense turbulent field of charged particles, distorting its path and frequency as it travels. But again, this would introduce chaos, not a clean, repeated cycle of changes. The thought then came up that FRB 121102 might be surrounded by a magnetic nebula, which is a very harsh environment that works like a filter or modulator. It is possible that the changing wavelengths are caused by changes in the medium. That being said, this brings up a question. Why does the material around the signal change in a pattern if it does change it? The word here is pattern. We know how to explain randomness. Repetition points to a deeper system. Some experts started to wonder what could be going on. What if this isn't just a normal signal? What if it was planned? Before anyone jumps to aliens, it's important to note that most astronomers still lean towards natural explanations. But the repeating cycle, frequency drift, and immense power of FRB 121102 remain incredibly difficult to reconcile with anything we've seen in astrophysics before. And when nature doesn't give us answers, imagination steps in. Some researchers have speculated about rotating neutron stars with processing axes, or magnetars undergoing irregular crustal shifts that alter emission paths. Others suggest we might be seeing interactions between exotic objects such as quark stars or primordial black holes, generating conditions unknown to current models. But no theory neatly explains all the facts. We're left with only some answers, unfinished math, and more questions than answers. What's even stranger is that other FRBs have since shown similar traits. For example, FRB 180916 also has a cycle that goes around and around with busy and inactive times. Some of them also show the same lower frequency shift. That means FRB 121102 isn't the only one. It's a new type of FRB that could be a group of cosmic things that no one knows about yet, or it could be a new way that physics works. These bursts have been picked up by Earth-based observatories like CHIME in Canada and the Arecibo Observatory in Puerto Rico before its collapse. And as more data is collected, it's becoming clear that FRBs are not just one-off events or exotic accidents. They are a consistent, loud, and active part of the universe, and we don't fully understand why. the quiet sector of the universe with no supernovae. One of the most basic rules of astronomy says that there should be noise in the visible world, but there is none. It's too quiet. Outside, space might look calm, but inside it's very dangerous, especially when it comes to the stars. Supernovae are the bright, burning deaths of stars that can be seen all over the world. These blasts are so strong that they can be seen from other galaxies for weeks. They send heavy elements into space, where they help make new stars and planets. Supernovae are a cosmic given. In a galaxy like our Milky Way, astronomers expect 1 or 2 supernovae per century. Multiply that rate across billions of galaxies, and it adds up to thousands of stellar detonations visible across the sky every year. Astronomers had a lot of questions when they found a part of the universe that didn't seem to have any supernovae. Researchers made a list of thousands of supernova events using survey data from projects like the Pan-STARRS telescope and the Sloan Digital Sky Survey. But in a section of deep space that was tens of millions of light-years long, they found almost no new supernovae. There were galaxies there. There were stars. Not a flash, though. Nothing blows up. There are no death throes of dying suns. This wasn't just a random coincidence. Even with conservative estimates, there should have been dozens of supernova within that region during the observational window. But there were none. Some galaxies in the region appeared older and more evolved, with fewer young massive stars, those most likely to go supernova. But that wasn't the whole picture. Some spiral galaxies within the void showed all the markers of ongoing star formation. These galaxies should have produced at least a few supernovae, but again, the sky remained silent. At first, scientists questioned whether this might be a case of observational bias. Perhaps dust or gas obscured the light. Maybe gravitational lensing or redshift made the supernovae harder to spot. But those theories didn't hold up. Observatories scanning in infrared and X-rays, wavelengths that can penetrate dust, also saw nothing. Next, researchers considered the possibility that supernova in this region might burn differently. Could they explode in ways that make them invisible? Could the dying stars in this region collapse directly into black holes without a bright flash? Known as failed supernovae, this idea has been proposed before, but only in isolated cases. For it to explain an entire region's silence, it would require a major difference in stellar evolution, isolated to one corner of the universe. There's also a hypothesis that ties this anomaly to metallicity, the abundance of elements heavier than helium in stars. Stars with very low metallicity are thought to collapse differently and may not produce standard supernovae. But galaxies with star formation usually generate heavier elements over time. The galaxies in this region didn't seem especially metal poor, so again, no clear explanation. If we stretch even further, we run into exotic physics. Some theorists have speculated that this area could be a region with weakened gravitational constants or differences in dark energy density, factors that could subtly alter the life cycles of stars. But these ideas remain on the fringe, unsupported by other evidence. What makes this quiet sector so unsettling is not just the lack of fireworks, it's what it suggests about cosmic variation. If the rules of stellar death aren't consistent across space, it challenges the core principle of cosmology, that the laws of physics are the same everywhere. Imagine trying to figure out how nature works if the gravity in your neighbor's backyard was different. So big is the amount of doubt this finding creates. Since this strange thing was first noticed years ago, new space telescopes, like the James Webb Space Telescope, and future projects like the Vera C. Rubin Observatory have been sent to look even deeper into this quiet area. The dark hasn't been lit up yet. But what if this silence is the result of a long-dead galactic collision, or an event that wiped out star-forming fuel long ago? Or worse, what if the stars are still dying, but doing so in ways we can't detect? That would mean our understanding of stellar death is dangerously incomplete. Unexpected thermal activity in the Kuiper belt. It should be cold in the Kuiper belt. It was really cold. The ring of icy objects in the distance goes past Neptune's orbit and is more than 4.5 billion kilometers from the Sun. Around here there isn't much sunshine, it's very cold, and everything, planets, moons, rocks and ice, should move slowly and silently. But something strange has been seen in the last few years. The Herschel Space Observatory and NASA's Spitzer Space Telescope picked up thermal signals, or heat, from things in the Kuiper belt that shouldn't be giving off any. Not just one object, but many things spread out in the area, such as dwarf planets, big asteroids, and even some smaller Kuiper belt objects, KBOs. Even though they don't get much sunlight, these tests show that some of them are warmer than predicted. What's making these frozen artifacts warm again? First, the math was checked by scientists. The Kuiper belt's thermal models are based on information that is already known, like its size, reflection, albedo, and the makeup of its materials. Most KBOs are covered in a dark dust that is high in carbon and doesn't absorb light very well. That means the surface shouldn't have enough energy to glow in the infrared range, even if it is dark. Still, it does. One leading theory is that some KBOs might have internal heat sources, not radioactive decay. That's too slow and weak at these sizes. Instead, researchers propose something more exotic: residual heat from ancient collisions, or internal crystallization processes that slowly release stored energy. But again, these are extremely long-term events. Most should have run their course billions of years ago. Another possibility is that some Kuiper belt objects may contain subsurface oceans or liquid pockets under a crust of ice and rock. This sounds wild, but it's not entirely without precedent. Moons like Europa and Enceladus, much farther in, have proven that liquid water can exist under thick layers of ice thanks to tidal heating and chemical interactions. Could similar mechanisms be at work in these distant icy bodies? The problem? The Kuiper belt doesn't have large gravitational partners to create the kind of tidal forces we see with Jupiter's moons. And most of the KBOs are far too small to retain heat that long, unless we're missing something major about their makeup. Another hypothesis: dark matter interactions. While extremely speculative, some physicists have proposed that dark matter particles passing through dense bodies like KBOs could occasionally interact and release minute amounts of energy. On Earth, this would be imperceptible. But in the cold vacuum of the Kuiper belt, even a small thermal boost could register in infrared. Some thermal emissions weren't just coming from deep within the objects, but from their surroundings. Instruments picked up faint signs of localized heating in space, near certain objects, almost as if there were thin, unseen atmospheres or exospheres temporarily forming and radiating heat. This could point to outgassing events, where buried volatile compounds like nitrogen or methane suddenly erupt from the surface due to internal pressure, creating temporary clouds of gas. Some KBOs might not be dormant at all if that's the case. They might be geologically active, but moving very slowly. These strange temperature events don't happen all the time. One season, an item might give off heat that can be felt, and the next it might be quiet. Not a pattern. There is no clear orbit-based cause. Something like a flashing light is happening in the darkest, deepest part of our solar system. NASA's New Horizons probe, which visited Pluto in 2015 and has since been traveling deeper into the Kuiper belt, added more fuel to the fire. It found that Pluto itself is more geologically active than anticipated, featuring vast glaciers, ice volcanoes, and a potential subsurface ocean. If Pluto can do it, maybe others can too. But not everyone is convinced. Some astronomers believe the infrared readings are being misinterpreted, perhaps caused by reflection effects, instrument noise, or background cosmic radiation. But cross-referenced observations from different instruments have repeatedly confirmed that something is happening out there. Something that shouldn't be possible, at least according to what we thought we knew. What do we still have? It looks like a place that was supposed to be a cosmic fridge is getting warmer than planned. There is heat where there shouldn't be any. There is noise where there should be quiet. There are also thermal patterns that point to something hidden below the surface of the solar system's most lost border. People have long thought of the Kuiper belt as a place where space junk and cold pieces end up, but it may be more living than dead. Not in the organic sense, but in the sense of how the Earth works, changing and moving. It was frozen in its way of breathing. A star that dims with no pattern, even from afar. Most stars are easy to guess. They shine steady, and if they flash or pulse, we can be very sure of how they do it. Some stars, like Cepheid variables, show time by how bright they are, but there is one star that doesn't follow the rules. Astronomers have been confused for years by how it does this. That star is Chi C 8462852, more famously known as Tabby's star. Located about 1,470 light-years away in the constellation Cygnus, it first caught attention during the Kepler Space Telescope's mission to find exoplanets. Kepler's method was simple. Stare at stars and wait for periodic dips in brightness, tiny eclipses caused by planets passing in front of their host stars. But Tabby's star wasn't acting like the others. It lost brightness all the time, not just in small, steady drops. Sometimes it was only 5%, and other times it was over 20%. To give you an idea, a planet about the size of Jupiter blocks about 1% of a star's light when it transits. A 20% drop then, that's really big, and these dips didn't happen at regular times like planetary transits do. They came out of nowhere, were different in length and intensity, and didn't follow a trend. Even more bizarre, some dips lasted for just a few days, while others stretched for weeks. In 2017, new observations revealed the dimming wasn't just occasional, it had been happening over centuries. Historical data from old photographic plates taken in the late 1800s showed the star's brightness had been steadily declining over time. A slow fade no known stellar process could explain. So what's causing it? The first wave of theories focused on natural phenomena. Could a swarm of comets be orbiting the star, spewing dust and debris as they disintegrate? That would explain the irregular dimming, if giant clouds of icy bodies were passing by. But for this to cause such significant dimming, you'd need an impossibly dense and massive cloud of comets, perfectly aligned with Earth's point of view, and that seemed unlikely. Then came the dust hypothesis. Maybe Tabby's star is surrounded by an uneven disk of interstellar dust, like a warped, clumpy version of Saturn's rings. Some evidence supported this. The dips appeared more dramatic in visible light than in infrared, which is consistent with fine dust particles blocking some wavelengths more than others. But even this explanation hits snags. For one, where's the source of the dust? There's no sign of a recent planetary collision or massive debris field. And why is the dust behaving so chaotically, orbiting in a way no model could recreate? Then there was the idea that made the news. What if it's fake? In 2015, a small but loud group of scientists, led by Jason Wright from Penn State, came up with a wild theory. The strange dimming could be caused by a megastructure, like an alien-built array or a Dyson swarm that is taking energy from the star. No one said this was the most likely reason, but it wasn't thrown out either. Radio telescopes were quickly directed at the star by SETI, Search for Extraterrestrial Intelligence, and didn't find anything. But even if there's no radio signal, the star's behavior still doesn't add up. Kepler saw more than 1,500 stars during its mission. None behaved like this. None dimmed this deeply, this unpredictably, or this consistently over time. Tabby's star is alone. Additional theories rolled in. Some proposed giant planetary rings, others suggested intervening interstellar clouds, and one even considered star-gobbling black holes obscuring the light from a distance. But none of them explain all the observed features. The depth of the dips, the lack of periodicity, the color-specific dimming, and the long-term fade. New information from the Gaia mission has added to the picture. It proved how far away the star was and helped figure out how bright it really was, which ruled out some crazy ideas. The mystery still stands. We could blame bad data if this was a one-time thing. What kind of star is it? If we knew, we could put it away as a strange but known object. But Tabby's star isn't any of those things. It's a great exception. A ghost light in space, blinking in the distance, following rules we don't fully understand yet. And it makes us think about tough things like, are our models of perfect behavior missing something? Are we unable to see whole groups of things because they don't fit our expectations? Symmetrical pulses from a distant magnetar. Magnetars put on the most dramatic shows in the huge stage of deep space. Neutron stars have magnetic fields that are so strong that they could wipe your credit card from 100,000 miles away. They are rare and unusual leftovers from supernova blasts. They are dense, dangerous, and often hard to predict. It's not the chaos of one magnetar that has NASA's attention. It's the strange, disturbing harmony of it. In 2020, astronomers monitoring distant X-ray and radio sources noticed a peculiar object. A magnetar located over 30,000 light-years from Earth was emitting precisely timed radio pulses. That alone wasn't unheard of. Magnetars can occasionally act like pulsars, sending out rhythmic beams of radiation as they spin. But these pulses were different. Instead of flickering like a strobe or sputtering like a damaged engine, this magnetar pulsed with almost musical regularity, like the ticking of a perfect cosmic metronome. And not just in timing, but in shape. The radio waves it produced formed symmetrical structures that mirrored each other almost identically, as if someone or something had designed them. The signal was first picked up by the Chime Radio Telescope in Canada, which is tuned to detect fast radio bursts, FRBs. Normally, FRBs are chaotic, short, powerful, and often one-off events. But this signal wasn't just repeating, it was folding. The waveforms mirrored themselves across time, suggesting an underlying order that natural astrophysical processes don't typically show. What made this even stranger was the magnetar's behavior across different wavelengths. In X-ray observations, it was active, flaring with bursts of high-energy radiation. In radio waves, however, it was whispering a pattern, one that repeated with clockwork precision over weeks, even months. Some scientists initially dismissed the symmetry as a coincidence, a trick of signal processing, or a side effect of our instruments. But when multiple telescopes confirmed the pattern independently, the anomaly grew harder to ignore. It was too consistent, too clean. Nature, while beautiful, is rarely this tidy. One idea put forward is that the magnetar's crust, strained by its magnetic forces, is cracking in a periodic way. These starquakes could send out symmetrical shock waves, modulating the radio pulses in a mirrored rhythm. But to maintain that symmetry over such long periods would require impossibly regular internal dynamics for an object spinning dozens of times per second. Another theory is that something is orbiting the magnetar, perhaps a ring of debris or a small planetary remnant, causing gravitational interactions that shape the outgoing signals. Yet no orbital model matches the timings perfectly, and infrared surveys around the object showed no sign of nearby material. There's also the chance that the signal isn't symmetrical at all, but only looks that way due to a bending of space-time. Magnetars can twist and warp the space around them, especially if they're rotating quickly. This could potentially cause gravitational lensing of their own emissions, creating echoes or mirrored waveforms as radiation takes multiple paths to reach Earth. Still, none of these theories make sense in every way. Which brings us to the main question, why is this magnetar different? A huge number of neutron stars have been studied. Many of them have bursts, flickers, or time that is all over the place. But none of them send out waves that are balanced like this one does. It would happen more often if it was a real trait of magnetars in general. Its isolation and stability point to either a unique internal system or a process that no one knows anything about. And of course, whenever radio symmetry arises in deep space, the question creeps in, is it artificial? Scientists are careful not to jump to conclusions. SETI researchers and astrophysicists alike have been burned before by natural phenomena that mimic artificial signals. But it's worth noting, one of the earliest proposed signs of intelligent life was narrowband, repeated radio emissions with mathematical structure. This broadcast is not carrying information. There is no message being sent, but the way it's shaped, its mirrored pattern, steadiness and lack of decay, has made some people wonder if it's not a noise signal after all. Right now, all we can do is watch. NASA and other space agencies are still keeping an eye on the magnetar and writing down and mapping every pulse and shift they see. The balance hasn't been broken yet. Like a heavenly heartbeat, it keeps going without stopping. Gravitational waves from no visible collision. One of the most important findings of the 21st century was gravitational waves. Einstein's theory of general relativity was the first to predict these ripples in space-time. They happen when very heavy objects, like black holes or neutron stars, meet. For years, that's exactly what we saw. Mergers that sent out short signals that could be picked up across the universe. But then, something strange happened. In late 2019, the LIGO and Virgo observatories picked up a gravitational wave that didn't fit the pattern. The signal, known as GW 190521, was strong, clear, and real. But there was a catch. No light followed it. No gamma rays, no X-rays, no optical flash, no afterglow, nothing. Typically, when neutron stars merge, or even when one crashes into a black hole, there's at least some form of electromagnetic radiation. Telescopes around the world go on alert, scanning the skies to capture the aftermath. But for this event, silence. This isn't just a lack of visibility, it's a missing footprint, like hearing a massive explosion in the distance, but arriving at the site and finding nothing. No debris, no smoke, not even a crater. Scientists went back over what they had done. First, they looked at the mass structure of the signal. The evidence from the gravitational waves showed that two very big black holes, each dozens of times heavier than the Sun, merged. In fact, one of them seemed to be in the mass gap, which is a strange area where black holes shouldn't form because of the limits on how stars can evolve. Just that made it strange. Then came the location issue. Using triangulation, researchers narrowed down where in the sky the wave came from. But despite pointing the most advanced telescopes we have, Hubble, Fermi, Swift, and dozens of others, no optical counterpart was found. This wasn't a one-time thing. A number of follow-up finds showed a rising pattern, gravitational waves that come from nowhere that can be seen, nothing to host. There was no light flash. It was just the universe twisting itself, coming like a ghost with no shadow. So what's going on? The leading theory is that some of these events are happening in completely dark regions, places filled with dust or gas that absorb all light before it escapes. But even in those scenarios, we'd expect infrared or radio emissions to leak out eventually, and they didn't. Another possibility? The mergers are occurring in intergalactic space, far from galaxies, in voids where stars are rare. That could happen if black holes are ejected from their home galaxies due to gravitational slingshots and drift for millions of years before finally colliding. But again, that raises questions about how these objects found each other in such isolation. Some physicists suggest that the mergers might involve primordial black holes, hypothetical objects formed not from dying stars, but from density fluctuations in the very early universe. These would be invisible by nature, never shining, never forming galaxies, simply drifting until the day they meet. One radical theory posits that we may be witnessing black hole mergers in extra dimensions, where only the gravitational waves bleed into our observable universe, while the collision itself happens somewhere beyond our space-time. This isn't mainstream science, but it's a possibility that's been explored in string theory and brain cosmology. There's also the quiet thought, what if these aren't really black holes? Some people think the gravitational waves could be coming from strange things we don't know much about, like boson stars, gravastars, or something completely different from our normal model. We wouldn't be able to see these in any range, but they could bend space-time in ways similar to black holes. What makes this even more unsettling is the frequency. We're not talking about one or two odd detections. We're now seeing a growing catalogue of gravitational wave events with no light signature and no obvious origin. It's as if the universe is speaking in a language we haven't begun to understand. What should we do? We pay attention. This time it's deeper, longer, and more carefully than ever. LIGO and Virgo are still getting better at being sensitive. The LISA project, which is a space-based gravitational wave monitor that will launch in the 2030s, may give us more information by following lower frequency waves from even stranger mergers. Strange lensing patterns in empty deep fields. Astronomers use gravitational lensing a lot to make maps of things that can't be seen. When a big object, like a galaxy or black hole, is between Earth and a light source further away, its gravity bends that light, making it bigger and wackier like a cosmic funhouse mirror. Einstein saw this coming, and space has shown him over and over that he was right. What does it mean, though, when lensing shows up where it shouldn't? This is the exact puzzle that scientists, looking at the Hubble deep fields and other very sensitive parts of space, can't figure out. These areas were picked because they look empty. They don't have any bright stars or big galaxies, so they're great for seeing into the farthest reaches of the universe. Still, scientists saw clear but faint lensing effects in some of these dark areas. Light from galaxies very far away is being bent, winding up to warp. What is it that is bending, though? It's not there, not a galaxy, not a cluster, no dark cloud. There is nothing that can be seen that could explain the gravitational mass needed to bend light in this way. There are ghosts of matter that don't interact with light, but are heavy enough to bend it. It's like the world is being pushed and pulled by them. To understand just how strange this is, consider the math. For light to bend in the way we've observed, it takes enormous amounts of mass. Not a rogue asteroid, not even a single star. We're talking the mass of thousands or millions of suns, positioned in just the right spot to create lensing arcs or stretched images of background galaxies. The most accepted explanation, of course, is dark matter, that elusive substance thought to make up about 85% of the matter in the universe. It doesn't emit light, doesn't absorb it, but it does exert gravity, so it could, in theory, cause gravitational lensing while remaining invisible. But here's the problem. The lensing patterns in some of these fields don't match typical dark matter distributions. They're too sharp, too focused, too localized. If dark matter is to blame, it's clumping in ways our models don't predict, forming compact, dense structures in regions we assumed were smooth and empty. One particular incident came from a study using the Subaru telescope in Hawaii, which imaged a field around an extremely distant galaxy cluster. In this field, multiple arcs of light were detected, clear signs of lensing, but the mass required to cause that effect didn't correspond with any known object. Even more puzzling, follow-up observations in multiple wavelengths, radio, infrared, X-ray, turned up nothing. So scientists began to wonder, could this be evidence of a dark galaxy? A structure made almost entirely of dark matter with little to no stars, a gravitational well without light. It's a theoretical possibility. Some simulations predict they should exist, but until now, no one had a clear signature of one. Another hypothesis is that we're seeing the effect of primordial black holes, possibly formed moments after the Big Bang. These wouldn't necessarily emit radiation or form galaxies, but they could still cluster in the voids of the universe. If a handful of them grouped close together, their collective gravity could produce lensing. But once again, that requires a very specific, very unlikely alignment. Even more speculative is the idea of massive compact halo objects, or MACHOs, an old-school alternative to dark matter that includes brown dwarfs, neutron stars, or black holes floating unseen in galactic halos. But MACHOs have largely fallen out of favor as a comprehensive explanation for dark matter, because we haven't found enough of them. Then comes the wildcard theory, lensing by cosmic strings. These are hypothetical defects in space-time itself, left over from the early universe. If they exist, they could bend light through gravity, despite having no mass in the conventional sense. Some of the symmetrical lensing arcs in deep fields almost resemble what a cosmic string interaction would produce, though that idea remains firmly in the highly theoretical category. The truth is, none of the explanations fully satisfy all the observations. We see arcs and streaks, clear signs of light being bent, but no lens, no object, no heat, just distortion, as if the cosmos itself is hiding something in plain sight. A black hole with no observable mass around it. Black holes are thought to be like cosmic vacuum cleaners that eat everything in their path, from gas and dust to whole stars. And when they're eating, they send out a huge amount of energy, mostly in the X-ray and ultraviolet ranges. They usually sit in the middle of galaxies, surrounded by matter that is slowly moving in toward them, even when they are not active. That's why the next finding was so strange. A black hole whose gravity was very clear, but it doesn't have any mass around it. Not at all. The discovery came from data gathered by the Very Large Telescope, VLT, in Chile, and confirmed by multiple instruments, including the Gaia Space Observatory, which tracks the motion of stars with incredible precision. A team noticed something odd. A group of stars was being pulled and twisted, as if something incredibly massive was nearby, yet nothing could be seen. Further study revealed that the gravitational tug on the surrounding stars corresponded to an object roughly 10 times the mass of the Sun, but with no light source, no heat signature, and no visible matter in the area. This wasn't just an empty patch of sky, it was an invisible force shaping stellar motion like a ghost pulling strings in the dark. Astronomers eventually concluded that this had to be a stellar mass black hole, left behind after the collapse of a massive star. But here's where things got weird. Where was the accretion disk? Where was the X-ray radiation? Where was the interstellar gas, the cosmic debris field, the traces of a violent collapse? All missing, completely. Black holes without accretion disks aren't unheard of, especially in quiet regions of space, but even those usually reveal themselves through subtle interactions, heating of nearby material, gravitational microlensing, or the presence of a companion star. This one, nothing. The black hole was essentially naked. Not literally, it was still cloaked in the event horizon that defines a black hole, but naked in the sense that there was no interaction with the surrounding space, just warping gravity, plain and silent. Think of it like a whirlpool in the ocean, with no swirling waves, no debris, no foam, just a sudden dip in the water that you only notice when a ship gets pulled sideways. Some scientists think that this item may have come together in a strange way. It could not have been formed by a supernova explosion, which leaves behind heat and light. Instead, it may have been formed by a direct collapse, in which a star simply collapses without going through an explosive phase. In theory, that would leave behind a black hole with no signs of what was there before. But things like that don't happen very often, and we've never seen one firsthand. Another hypothesis is that the black hole might have been ejected from a dense cluster, or even from a galaxy itself. If two black holes merge and send out gravitational waves in one direction, conservation of momentum can fling the remnant in the opposite direction, at speeds of hundreds or even thousands of kilometers per second. This recoil could have sent it sailing into interstellar or even intergalactic space, leaving behind all the gas and stars it once orbited. But even if that were true, the object would still interact with the occasional particle or cosmic dust cloud. It would eventually build up a faint accretion disk, even if just a whisper of one. Yet no trace of such a structure has been found. This leads to the most intriguing possibility. Perhaps the black hole is surrounded by something we can't yet detect. Could it be interacting with dark matter, absorbing it without the electromagnetic emissions we're used to? Or is there a new class of compact object we've never classified? Something that mimics the gravitational signature of a black hole, but behaves differently. A fringe theory even suggests that this might not be a black hole at all, but a gravastar or boson star. theoretical entities that have the mass and gravitational pull of a black hole but lack an event horizon. These exotic objects could explain the absence of radiation while still producing the gravitational footprint observed. But without direct evidence, it remains speculative. No matter what the answer is, it has huge effects. There may be thousands or even millions more of these huge objects floating through the Milky Way if they can exist without being seen, heard, or felt by anything other than their own gravity. Assassins of space who are invisible to us because they move between stars and bend light and motion while hiding from every camera we have. Using stellar motion studies and gravitational microlensing programs, NASA, ESA, and telescopes around the world have stepped up their efforts to find more of these objects. They want to get a better look at gravity's shadowy messages. Time dilation near a quasar that breaks relativity. A quasar is one of the biggest and farthest things in the universe. They shine with the power of trillions of stars squished into a space no bigger than our solar system. This power comes from supermassive black holes at the centers of faraway galaxies. We can see them from billions of light years away because they are so bright. They're like windows into the early universe. They also follow the rules, the very least they should. But in one strange case, a quasar didn't just give off strange light, it seemed to mess with time in a way that goes against Einstein's theory of relativity. The strange thing was found during a time domain study that used information from pan-stars, Sloan Digital Sky Study, and XMM Newton. Over the course of several years, astronomers looked at a faraway quasar to see how its light changed. Because of cosmological time dilation, these light patterns seem to move more slowly the farther away a quasar is. This is because cosmological time dilation says that the faster something moves away from us, the slower time seems to pass for it. This is baked into the fabric of the universe's expansion. It's why, when we look at a quasar 10 billion light-years away, its light seems to flicker more slowly than one just 1 billion light-years away. But this particular quasar, catalogued as J043947.08 plus 163415, 7 didn't play by those rules. It pulsed like it was right next door, even though it's located over 12 billion light-years away. Its periodic brightening and dimming occurred on timescales that completely ignored redshift effects. No stretching, no slowing. It behaved as if time dilation had taken a day off. Some theorists proposed that this quasar might be part of a gravitational lensing system, where its light is being distorted or magnified by a foreground object, that could, in theory, mess with the way we perceive its flickering. But follow-up observations found no evidence of lensing. The light wasn't split, mirrored, or magnified in the ways we'd expect from such a system. Another possibility. The light wasn't coming from a single object, but from multiple quasars overlapping in our line of sight, creating an illusion of strange timing. Yet spectral analysis showed the emission lines were too consistent, a single set of fingerprints from a single source. Do you think Einstein is wrong? Not in a broad sense. Every big test we've given it, from finding Mercury's path to gravity waves, it has passed. But new physics might be ready to be discovered in very strange places, like the edge of a black hole or the center of a quasar. Some researchers think this might be because of how time dilation and quantum fluctuations interact. Or it could be because Lorentz invariance breaks down at very high energies. Others floated the idea of tachyonic fields, hypothetical particles that always move faster than light and might warp the perception of time in their vicinity. These belong to the realm of fringe theory, but when an object 12 billion light-years away is flickering like it's a neighbor, you don't ignore the weird ones. There's also the potential involvement of extra dimensions. In some versions of string theory, gravitational and temporal effects can bleed across unseen dimensions, subtly altering the flow of time in ways our instruments can't yet decode. If this quasar sits near a cosmic defect, like a brane intersection, its time signature might be distorted in ways that appear nonsensical from our four-dimensional perspective. As the study of time domain astronomy gets better, Scientists have found a few more quasars that don't seem to bend time. Not all to the same degree, but enough to make you wonder. Enough to make it seem like this wasn't a coincidence. What do we still have? A thing from the beginning of time that is flashing in your garden like a strobe light. A rejection of time, coming from something so far away that its light left Earth before it was even known as Earth. This quasar is the broken part of the universe's clockwork that we don't know how to fix, or even if it needs to be fixed. Upcoming telescopes like the Vera C. Rubin Observatory and James Webb Space Telescope are expected to monitor thousands more quasars with unprecedented detail. Maybe we'll find a pattern. Maybe we'll uncover a new law of physics. Unstable orbits in a supposedly stable cluster. In the universe as big as the universe, steadiness is not the norm but the exception. Stars are born, live short lives, and die quickly. Galaxies hit each other. Black holes eat things. Still, some star clusters, ancient groups of stars that are held together by gravity, seem to defy that order. They dance through the universe in patterns that have been there for billions of years and are perfectly timed. In a globular cluster known as NGC 6752, located about 13,000 light-years away in the constellation Pavo, something is wrong. This cluster, like many others, is densely packed, containing hundreds of thousands of stars in a sphere just a few dozen light-years across. These types of clusters are believed to be among the oldest structures in the universe with well-understood orbital dynamics. The stars inside should follow predictable paths governed by Newtonian and relativistic gravity. But when researchers mapped NGC 6752 with high-precision data from the Hubble Space Telescope and the Gaia Observatory, they discovered something shocking. A number of stars were drifting, accelerating, or veering off course in ways that didn't align with the cluster's gravitational model. The orbits were supposed to be stable. Instead, they were subtly but consistently unstable, like marbles rolling on a warped table, slowly drifting away from where physics says they should be. At first, scientists suspected instrument error, but the data checked out. Multiple telescopes confirmed the phenomenon. Then came a more unsettling possibility. Something massive, dark, and unseen might be hiding in the core of the cluster, distorting the gravitational landscape like an invisible anchor tugging at the stars. A prime suspect? A black hole. Not a stellar mass one, but an intermediate mass black hole, the missing link in the cosmic zoo. These hypothetical beasts are bigger than your average collapsed star, but smaller than the supermassive giants that sit at the hearts of galaxies. They've long been theorized but never directly observed. NGC 6752 could be housing one, or more than one. However, simulations showed that even a black hole of moderate mass wouldn't cause this level of orbital decay. The star's movements didn't align with what you'd expect from a compact central mass. Instead, they hinted at something more diffuse, a non-uniform distribution of dark matter, or worse, a breakdown in gravitational theory at small scales. Alternative gravity models, such as modified Newtonian dynamics, MOND, or emergent gravity, have occasionally been invoked to explain galaxy rotation curves without dark matter. Could they also explain why stars in this cluster refuse to stay in line? Possibly. But those theories often fail under the dense and chaotic conditions of globular clusters. Another possibility is that some stars are being kicked out by repeated three-body interactions, where close gravitational encounters between two stars and a third object can fling one of them outward. But these types of interactions happen in small numbers and wouldn't account for the large-scale instability observed across the cluster. The most bizarre thought, that the cluster could be going through a gravity wave, which is a ripple in space-time that is strong enough to move the stars slowly over long periods of time. We know gravitational waves exist because LIGO and Virgo have found black holes and neutron stars meeting in the past. But the waves we've seen are very short. They only last a few hundredths of a second. A long-lasting wave strong enough to change the positions of a whole cluster would need an unimaginably large event. like the slow dance of two supermassive black holes getting ready to join, or something completely different. Some researchers now suspect that the cluster might be embedded in a larger, invisible structure, possibly a halo of exotic matter or a filament of the cosmic web. These massive tendrils of dark matter stretch across the universe, and their gravitational influence can subtly warp nearby regions of space. If NGC 6752 is caught in one of these currents, it could explain the erratic stellar motion without violating known physics. But again, the models don't quite fit. The drift patterns are too clean, too coordinated, too purposeful. It's as if something is actively shaping the orbits with intelligence, or at least with intent, like a sculptor gently pressing a finger into soft clay over millions of years. Exoplanet with a ring system larger than a star. Everyone knows Saturn for its thin, beautiful rings. But what if I told you there was a world with rings that are so big they could cover a star, not in a figurative way, to the point they cast shadows that are light years across because they are bigger than the width of our sun? We also didn't find this world because we saw it. It was huge and blocking starlight in a way that no known planet or moon had ever done before. The discovery began with data from the SuperWASP survey, which monitors stars for transiting exoplanets. One particular star, J1407, caught astronomers' attention back in 2007. It dimmed, not just a little, but in an incredibly complex pattern that lasted for 56 days. Brightness dropped, returned, dropped again, flickered and pulsed. It looked nothing like a standard planet transit. A normal exoplanet blocks a small portion of starlight as it passes in front of its host star, creating a clean U-shaped dip. But J1407's light curve was a jagged mess, like dozens of transits overlapping, with varying depths and durations. Something immense and intricate was in the way, and whatever it was, it had structure. Astrophysicists at the University of Rochester dug into the data and proposed something wild. A planet with a ring system over 200 times the size of Saturn's. That's not a typo. If Saturn's rings stretch roughly 280,000 kilometers across, this object's ring system spanned almost 120 million kilometers, nearly twice the distance from Earth to the Moon. The hypothetical planet, nicknamed J1407b, is thought to be a gas giant, several times the mass of Jupiter. But its rings aren't just oversized, they're detailed. Based on the dips in light, researchers estimate over 30 distinct ring bands, separated by clear gaps. These gaps likely point to exomoons, natural satellites sweeping through the rings, carving out paths just like Saturn's moons do. The scale of this ring system makes it impossible to survive around a planet in a tight orbit. It would be shredded by tidal forces or gravitational pull from the nearby star. That means J1407b has to orbit far from its host star. So far, in fact, that it takes decades to complete one orbit. That explains why the transit lasted nearly 2 months. The rings are so wide, it takes that long for them to pass in front of the star. It hasn't gone by since. Astronomers have been keeping a close eye on J1407 since 2007 because they want to see a second eclipse that will prove the path and presence of this ringed world. But nothing. It hasn't happened again. Earth might be out there, slowly moving through its path so that it only comes into view every 50 to 100 years. It's almost impossible to study at the same time. We only have that one beautiful and strange journey. One picture of something so big that it looks like Saturn. There was a moment when the stars lined up just right, showing us what planetary systems could become. Some have speculated that we caught J1407b in a transitional phase, a young planet with a ring system that will eventually collapse into moons, just as scientists believe Saturn's rings may have done long ago. Others wonder if it's not a planet at all, but a brown dwarf, a failed star with a complex accretion disk masquerading as planetary rings. The ring material itself is a mystery. Is it ice, rock, dust? If it's icy, it wouldn't survive long so close to the star. yet the transit suggests it's partially opaque, blocking significant starlight. That implies density, mass, substance, and structure. J1407b remains the most compelling case for an X-O-ring, a ring system outside our solar system. And it raises haunting questions. If we caught this one by sheer luck, how many others are out there? Are these massive rings common in young planetary systems? Do they all eventually break apart into moons? Or are some just so remote, so massive, and so distant that they never change? Eternal cosmic halos circling worlds we'll never see. Solar particles reversing direction in deep space. By the time you reach the edge of our solar system, things are supposed to calm down. No more solar flares, no more planet-sized magnetic fields, just the slow trickle of solar wind, particles flowing outward from the sun, gradually thinning into the void. At that distance, space is quiet, but Voyager 1 says otherwise. Launched in 1977, Voyager 1 is now over 14.8 billion miles from Earth, so far away that the signals it sends take more than 22 hours to reach us. In 2012, it became the first human-made object to enter interstellar space, passing beyond the heliopause, the invisible boundary where the sun's influence gives way to the interstellar medium. It was supposed to be the end of solar dominance. Beyond that threshold, the sun's magnetic field should be weak, and the stream of charged particles, protons, electrons, and alpha particles, should flow in only one direction, outward, away from the sun. But in 2020, something strange happened. In a quiet region of deep space, Voyager 1 detected solar particles that weren't escaping. They were coming back, reversing course, moving inward, toward the sun, in defiance of the very force that launched them outward in the first place. This wasn't a minor fluctuation. The reversal was clear and sustained. Voyager 1's cosmic ray subsystem registered low-energy particles that had no business being there, particles that should have been swept away by the solar wind years ago. It was as if something out there had reflected them back. Scientists scrambled for an explanation. One idea is that the particles were encountering a shockwave, a ripple in the interstellar medium caused by solar activity from years earlier. The sun sometimes unleashes coronal mass ejections, massive outbursts of plasma that can travel for billions of miles. If one of these waves collided with the interstellar medium, it could reflect particles backward, bouncing them toward Voyager 1 like a cosmic echo. But that doesn't fully explain the energy levels or the timing. Others proposed a more radical idea. Voyager 1 might have entered a region of magnetic draping, where the sun's magnetic field is tangled and twisted by its interaction with the galactic environment. In this boundary zone, magnetic reconnection events, where field lines snap and realign, could create particle flows in all directions, a kind of turbulence on a galactic scale. This would imply that the heliopause isn't a clean shell like we once believed. Instead, it's messy, dynamic, alive, like a soap bubble flickering at the edge of a storm. But here's the kicker. Voyager 1 also picked up plasma oscillations during this period. This tells us the local electron density was rising, and that could mean one thing. Voyager was moving through a structure, a pocket of denser interstellar plasma that somehow bounces particles back toward the inner solar system. No one knows what this structure is. It doesn't appear to be a cloud. Like the local interstellar cloud, we believe the solar system is currently passing through. It's more like a filament, a strand of matter woven into the fabric of the galactic medium. And it's not just reflecting particles. It might be trapping them, bending them, reshaping the entire local particle environment. The implications are enormous. If particles can be reflected or rerouted this far from the sun, our models of cosmic radiation exposure need a serious update. That matters for deep space missions. Astronauts headed to Mars or beyond could face higher or more unpredictable radiation levels than expected. It also suggests that interstellar space isn't a neutral vacuum. It's structured, active, and possibly dangerous. Magnetic fields, particle streams, and invisible walls may shape the outer environment in ways we're only beginning to understand. And what about Voyager 2? It's on a different path, farther south relative to the solar equator, but it hasn't reported the same reversals. That supports the idea that Voyager 1 hit a localized anomaly, not a solar-wide phenomenon. It found something specific, something unique, a cosmic cul-de-sac where physics turned inward. The particle reversal episode lasted several weeks. Then, just like that, things settled. The particles resumed their expected flow, but Voyager had already seen too much. It had captured evidence that the edge of our solar system is not a clean boundary. It's a war zone. A tangled no man's land where particles don't just leave. They get caught, twisted, and sometimes thrown back. Voyager 1 will keep flying. It has enough power to operate at least one instrument until around 2026. After that, it will fall silent. But its strange encounter with reverse solar particles will remain a clue, one more piece of the puzzle about what lies beyond the sun's reach. Because space doesn't always play by the rules. Sometimes even the most basic assumptions, like the direction of a solar wind, can turn around and point back at you. Infrared signatures matching nothing in our database. In many ways, astronomy is like going to the movies at night and hearing a symphony. You read what's out there through radio waves, gamma rays, X-rays, and infrared. You don't always see it. The electromagnetic range is made up of different parts that speak to us in different ways, and IR is the strongest of all of them. It helps us find heat in the coolest, lightest things, things that glow instead of shine. So when NASA's Wide Field Infrared Survey Explorer, WISE, and later Spitzer Space Telescope started scanning the sky in infrared, scientists expected a treasure trove of stars, galaxies, dust clouds, and distant planets. What they didn't expect were dozens of infrared objects that didn't fit any known pattern. There were no stars here. They weren't really galaxies. Even better, they weren't bad worlds. The colors and intensities of the infrared light they gave off didn't match anything in the astronomical databases that were already out there. Looking at it was like seeing a thermal picture of something real but unknown. Some of these things flickered as they gave off a faint glow. Some stayed the same. Some of them moved a little over time, which meant they were farther away than comets, but closer than stars. Still, they couldn't be seen at all in optical bands. It seemed like they were only in heat and not light. One such object, catalogued as WYSI AJ085510.83-071442.5, initially confused astronomers because of its extremely low temperature, around 54 to 9 degrees Fahrenheit. That's colder than the freezing point of water. A star can't be that cold. Even a brown dwarf, an object too small to ignite fusion like a true star, typically runs hotter than that. But this thing was barely warmer than liquid nitrogen. Eventually, WYSI AJ0855 was identified as one of the coldest brown dwarfs ever found, bordering the definition of a free-floating sub-brown dwarf or planetary mass object. But others remained unexplained. A growing list of infrared anomalies began populating scientific catalogues, many of them designated simply as unidentified infrared sources. What then could they be? Some scientists think these might be protoplanets, which are planets that are still in the early stages of formation and are covered in thick dust that blocks all light, except for the infrared light that comes from their heat as they grow. Some people think they might be failed stars, things that were never fully formed and now float as cold, dark shells. One idea posits that these anomalies are actually dark galaxies, collections of dark matter and gas that never formed stars. If they contained enough ambient heat or experienced occasional collisions, they might emit faint infrared signatures without being visible otherwise. Another fringe theory: extraterrestrial megastructures. Some physicists, particularly those in the field of Dysonian SETI, argue that advanced civilizations might build structures that emit waste heat in the infrared spectrum. A Dyson sphere or swarm, for example, would absorb a star's light and radiate excess heat, potentially matching some of the anomalous readings from WISE and Spitzer. Of course, there's no solid evidence for that yet, just unusual data points. But even without aliens, the mere fact that we've found dozens of objects that fit no known profile suggests something bigger. We may be blind to entire classes of celestial phenomena. As Spitzer's mission ended and WISE was put into hibernation, and later revived as Neo-WISE, the window for studying these anomalies narrowed. Some sources have since vanished, no longer visible even in infrared. Others remain fixed, silently glowing like cosmic embers with no clear origin story. The James Webb Space Telescope, with its unparalleled infrared sensitivity, offers new hope. Already it's peered into star-forming regions and exoplanet atmospheres, but it may also help solve the mystery of these infrared phantoms by dissecting their heat signatures at far finer resolution. The things in this story are interesting, but what they stand for is even more interesting. The sounds aren't very loud, they're not going off, they're not exciting, but they keep trying. In their soft, warm glow, they say that the universe still has types of matter and energy that we haven't even thought of names for yet. A spiral galaxy rotating the wrong way. Galaxies are like pinwheels in space. They are huge swirls of stars, dust, and dark matter that move through space in beautiful, regular ways. The basic rule that most of them follow is that their spiral arms and the way they spin are lined up because of how they formed, how their stars collapsed, and the angular momentum they got from their birth cloud. That is, the direction of spin is not a coincidence. It shows what they have done in the past. What happens when a star spins around the wrong way? This is exactly what scientists saw when they looked at NGC 4622, a spiral galaxy in the constellation Centaurus that is 111 million light-years away. At first glance, it seems like nothing's wrong, just another lovely dance of stars caught by the Hubble Space Telescope. The problem was that its spiral arms on the outside seemed to be spinning in the opposite direction of its disk on the inside. Now, this shouldn't be possible. Imagine a vinyl record playing on a turntable, and the outer edge starts spinning counterclockwise while the center spins clockwise. That's what's happening with NGC 4622. It's not just weird, it's fundamentally at odds with how galaxies are supposed to behave. In typical spiral galaxies, the arms trail the direction of rotation. If the galaxy spins clockwise, the spiral arms curl behind it in that same direction. But in NGC 4622, the outer arms appear to lead the spin. That led to a burning question. Is the entire galaxy rotating backward, or are just some parts misaligned? Astronomers looked at Doppler shift data, which is a way of tracking how light from different parts of the galaxy is stretched or squeezed based on motion. They were shocked by what they found. The galaxy's center spins in one direction, while its arms move in the opposite direction. It looks like the heart and the outer ring don't agree on which way time should go. How could this happen? One explanation is a galactic collision or merger. If NGC 4622 collided with a smaller galaxy that came in at just the right angle and speed, it might have transferred enough angular momentum to flip the rotation of the outer disk, while leaving the core spinning the original way. Essentially, the galaxy was hit so hard in one direction that its outer regions started spinning backward. Another idea is that the galaxy slowly took in outside matter over billions of years, like gas or small satellite galaxies. This is called a cosmic accretion event. If that stuff came in from the other way, it might slowly change how the outer disk spins. It doesn't look like it was recently hurt. There are no tide tails, no broken pieces left behind, no bright marks from a fight across the galaxy. It looks nice, equally sized, peaceful. However, it's turning in a strange way. A very small number of galaxies have seen this happen. There is one that stands out though, and that is NGC 4622. The evidence is solid, so it's not just a matter of how it was interpreted. There was something that broke the rules in this part of the universe. Galaxies that rotate the wrong way could also have implications for galactic evolution models. If retrograde spiral arms are more common than we think, it would mean that galaxies interact more violently and more often than our simulations predict. It would suggest the cosmic environment is more chaotic, more collision-prone, and more prone to angular momentum swaps than we've accounted for. Some researchers have wondered whether these anomalies could point to variations in dark matter distribution, the invisible scaffolding that holds galaxies together. If NGC 4622 has a warped or asymmetric dark matter halo, it could cause gravitational effects strong enough to twist the outer regions into reverse rotation. In any case, this isn't just a strange thing to look at. It's a test of our knowledge of how galaxies work. A spiral galaxy is a very carefully tuned balance of the forces of gravity, the formation of stars, and the preservation of rotational momentum. If you mess with one part of the system, it should start to fall apart as a whole. NGC 4622 is steady though. As if nothing is wrong, it keeps turning, living, and shining. A star ejected at impossible speeds. Most of the time, stars don't run. They circle, they float. They move with the galaxy's gravity, which makes it move slowly and gracefully. Even when they're going really fast, like a few hundred kilometers per second, it's still about what we would expect. That's why astronomers were shocked when hypervelocity stars were found. However, there is one that seems to go faster than the speed of light itself. Meet S5HVS1, a star in the constellation Phoenix that is about 29,000 light-years away from Earth. They used the Southern Stellar Stream Spectroscopic Survey, S5, to measure its speed in 2019, and found it to be an amazing 1,755 kilometers per second, which is almost 4 million miles per hour. To put that in perspective, it could travel from the Earth to the Moon in under 6 minutes. It's more than 10 times faster than the typical star in the Milky Way. At this speed, S5HVS1 isn't just going fast, it's escaping completely. It's on a trajectory that will launch it out of the galaxy entirely. Then how does a star get thrown away that fast? The Hills mechanism is the only known way for this to happen. Astronomer Jack Hills came up with this idea in the late 1980s. It says that if a binary star system, two stars following each other, gets too close to a supermassive black hole, the strong gravitational pull can tear the pair apart. One star is sucked into the black hole and put into orbit around it, while the other is sped away very quickly. That's exactly what astronomers believe happened with S5HVS1. Based on its trajectory, it was flung out from the center of the Milky Way, home to Sagittarius A star, a black hole with a mass 4 million times that of the Sun. This would make S5HVS1 the smoking gun of the Hills mechanism, the first direct observable evidence of a star being yeeted from the galactic center like a cosmic cannonball. But even that theory raises more questions than it answers. First, the age and type of the star. S5HVS1 is a young massive star, an A-type star, several times larger and hotter than our Sun. But most stars near Sagittarius A star are older. For a young star to have formed in the chaos of the galactic core and then been ejected with surgical precision is statistically odd. Second, the precision of its ejection. The star's path is remarkably clean. No evidence of gravitational interactions with other objects. No lingering orbital wobble. It's as if the black hole launched it perfectly, with just the right force and angle to exit the Milky Way. And third, there's the problem of how often this should happen. If Sagittarius A star is capable of flinging stars like this, we should be seeing many more hypervelocity stars. Yet so far, confirmed cases remain extremely rare. Some have proposed more exotic mechanisms. Could dark matter interactions in the core of the galaxy create extreme accelerations under the right conditions? Could we be seeing the result of an encounter not with one black hole, but two? A binary black hole merger that violently expelled nearby stars? Or stranger still, Could there be unknown forces at play in the galactic center? We know that Sagittarius A star is surrounded by dense stellar clusters, magnetic turbulence, and intense radiation. Some theories even suggest it might be orbited by an intermediate mass black hole or exotic compact objects, making the region a gravitational slingshot zone unlike any other. Whatever the case, S5 HVS1 is doing something our models didn't fully predict. It's on a one-way trip out of the Milky Way into intergalactic space. It will wander the cosmic void, cooling over billions of years, shining alone between galaxies. A distant object that reflects light but emits none. If something shines in the dark, cold space between the stars, it's either giving off light because of its own energy, like stars and quasars, or it's bouncing light from somewhere else, usually another star nearby. But in 2018, scientists looking at a deep field scan found something that didn't act like either of those things. It reflected light, but didn't emit any detectable radiation of its own. No thermal signature, no X-rays, no ultraviolet, not even a whisper of heat in the infrared. It was as if the object existed solely as a mirror, suspended in a lightless vacuum, bouncing back energy from something we couldn't see. The discovery came from a team working with data collected by the Subaru telescope in Hawaii and confirmed by follow-up observations from Hubble and Spitzer. What made the object so strange wasn't just its reflective properties, it was where it was found. In a region of intergalactic space completely devoid of stars. No galaxies, no light sources nearby, just the black of space and this ghost of an object glowing faintly in reflected starlight. Astronomers estimated it to be at least 50,000 light-years from the nearest visible star or galaxy. And yet it glimmered, very faintly but undeniably. That ruled out most natural causes. Comets, for example, can reflect sunlight, but only within solar systems. Dwarf planets and asteroids? Same story. Rogue planets? They typically emit some level of infrared heat from their core, especially if they've recently formed. But this thing didn't give off any sound. It wasn't even big. The object is thought to be about 10 to 20 kilometers across, which is about the size of a small asteroid, based on how much light it reflected. That quickly cut out a lot of the big, powerful options like neutron stars or black holes. Those do not reflect light, they bend it. So what could this be? The first and most cautious theory is that it's a stripped core, the metallic remains of a once larger body that's been ejected from a galaxy. Picture a planetary remnant made of pure metal or ice, polished over time by radiation and micrometeoroids, until it acts like a cosmic mirror. Another idea is that it's a fragment of a disrupted white dwarf flung into deep space during a supernova or binary star collision. But even then, such an object would normally retain some heat signature. Yet this one remains stubbornly cold. One of the more intriguing hypotheses is that it's surrounded by a form of ultra-reflective dust or crystalline material, possibly even exotic compounds, unknown to Earth-based chemistry. If so, it could represent an entirely new type of interstellar body. A few SETI researchers have pointed out that something this small, this cold, and this reflective could resemble an artificial construct, a probe, a remnant, a piece of debris from something intelligent, if not necessarily from our galaxy. After all, humans have launched metallic reflective spacecraft into space. Could other civilizations have done the same? And could we be seeing the sunlight bounce off the skin of a long-abandoned relic? Before we get to the aliens, though, there's a more realistic angle that's even scarier. What if we didn't count all the cold, light-reflecting things that are floating around in space? There could be thousands of quiet, dark things moving between every star and galaxy that is shining. These could be asteroids, planetesimals that have been left alone, or metal pieces from past cosmic crashes. We're only just beginning to catalogue such objects. Most sky surveys are tuned to detect light emission, not reflection, and certainly not reflection from far-off non-illuminated regions. What makes this particular object so chilling is that we only saw it by accident. It was in the background of a totally unrelated observation, picked up because a faint glint moved slightly between frames. If it hadn't reflected light at just the right moment, in just the right angle, it might have gone completely unnoticed, forever. There's no name for this object yet, only a catalogue number and coordinates. Follow-up attempts to relocate it have yielded mixed results. It may have moved, or dimmed, or tumbled in a way that its reflective surface is no longer aligned toward us. Space seems cold and empty to us. The truth, on the other hand, is much stranger. It's full of puzzles that don't fit our models and signs, that come from beyond what we can understand. These 35 cases are not made up. They are real findings from real trips. When someone says, "We know everything about space," just show them this list. As we reach the edge of what we can touch, the world still holds its most important secrets. You've come to the right place if you want to keep following them. Sign up for Beyond Horizons and stay weird with us.